Okay, we're beginning the reading on valuation of contingent claims. And during the last reading, for those who were attentive enough, you may have noticed that I didn't like all the notation that the author used during that chapter, and I simplified as best I could the notation while still being able to solve all the problems. In this chapter, I don't mind the notation. The notation is not ridiculous. It is pretty much in line with what you'd expect, so I'm going to stick with the notation. However, it is all the negative and plus signs that the author wants to use that are really, really annoying because they're not necessary. The author is telling the story during this chapter from a perspective of cash flows. So that a negative means it's a cash flow out. A positive means it's a cash flow in. Typically, we would look at negatives and positives in a situation like this in terms of positions, such that a negative meant a short position and a positive meant a long position. In this reading, it means exactly the opposite. A negative means a long position and a positive means a short position because you got to think about it in terms of cash flow. So when you see a negative sign, you got to say, first of all, well, that's not a short position. You have to say a negative sign means I put out cash. If I put out cash, I must have bought something. If I bought something, I must be long. To me, that's a huge waste of cognitive energy when you could just write this out in terms of positions and be done with it, and just be done with it. But if the author did that, then his textbook or his chapter would be no different than another well-written chapter, in which case, what value is he adding? So he decides saying, hey, you know what? I'm going to write my chapter from the perspective of cash flows. It'll be confusing for the student with all those pluses and minuses, but I will be unique and I will be distinct. Screw the student. I need tenure. I got to have a chapter. So here we are. But you know what? I'll explain the pluses and minuses, and hopefully we'll get it. Once you get deeper into the two-period binomial model, those pluses and minuses, especially during interpretation, are a real pain in the ass. A real pain in the ass because it slows you down dramatically. I'm going to show you a way around that, all right? So that we can keep the notation in this chapter, but temper all these pluses and minus signs. Here we go. Let's just start. What is our job? First of all, our job here is to make the argument for a no arbitrage price for a call, for an option, for any contingent claim. So we're going to start with a call, and we're going to show you how the argument is structured such that the call will be a no arbitrage price or a no arbitrage value on the call. We're not going to really prove that it is. We're just going to make the same argument we made in the last reading, that if a certain condition doesn't hold, there will be arbitrage, and somebody will step in and change that so that it's gone. That's all we want to do. So here we are. Let's start over here, and I'll see if I can get through this rather quickly. What do we have here? We have negative delta S and plus C. The delta will mean how many shares of the stock. S is the price of the stock. Delta will stand in for how many shares we buy. I deviate from the chapter here. The chapter uses H, meaning a hedge ratio. It calculates a hedge ratio, and H is the number of shares it buys and sells. I use delta because delta is one of the Greeks we have to deal with later on in Black-Scholes. And by using delta now, I'm going to give you the meaning of delta, which is exactly what the meaning of delta is later on. Later on, we have to turn the H into a delta. So I say, why not just start with delta and screw H? Get rid of H. It's not a hedge ratio, it's a delta. Use that. So what does this mean, negative delta S and plus C? Well, plus C means we got the value of the call. C is the value of the call. So we got it, which means we must have sold it. So plus C means we're short a call. Negative delta S means we're long the underlying shares. You see how confusing that is? Wait till later on when you go 2 periods in and you have to figure out what's going on with all these negatives. There's one place where you have a negative and inside the delta is another negative, and you have to remember that a negative is a plus, so that you're actually long and not short. It is a real pain in the ass. Anyways, fine. The author wants to go with cash flows. Let's just humor him for a bit. So there we go. So that's what we've got. We're short the call, and we're long the underlying shares. We can have two moves. You can have an up move or you can have a down move. If we have an up move, this now is just in terms of value. What is the value of our position? It'll be S plus and C plus. The value of the underlying will be S plus. The value of the call will be C plus. Not saying whether we're up or down on this, just the value of it. And the value of our position on the downside is delta S minus, C minus. Just introducing notation. So that when we see a plus sign, we know that that was the value after an up move. If you see a negative sign, that was the value after a down move. Our delta, which tells us how many shares we want to have, is calculated as the value of C of the call after an up move minus the value of the call after a down move divided by the same ratio with respect to the shares. And what does delta tell us? It tells us the change in option price to the change in stock price. Guess what? That's delta. We just translated one of the Greeks later on. That's delta. If you buy an option that has a delta of 0.62, what that tells you, it's the same thing as owning 62 shares. It would be the same thing as owning 62 shares. Another way to say it is, if the underlying stock price goes up $1, the option price will go up 62 cents. That's what delta is. So why call it H when later on we're going to call this very same thing delta? I say let's call it delta right from the start. This is not a mystery novel. There's no whodunit. Give me all the characters up front. There we go. Okay, so what is our payoff? Our payoff after an up move is we get to sell the shares. How many shares? Delta shares. So we'll sell delta S plus. S plus is the price after it's gone up. We'll realize that much. But we got to lose money on the call, because if we sold a call, it hurts when it goes up. We're short the call, so any up movement in price hurts us, minus C plus. And of course, on a down move, it's delta S minus. We'll get this much after selling the shares, minus C plus, the value of the option. Well, the value of the option will be 0. Now, keep in mind, we're not interested in the profit of the position at this point. We're interested in the payoff of the position. Now, we sold the call for something, yes, but that will not be wrapped up in the payoff. That will be wrapped up in the profit. This is just the payoff of the position. The reason we can't figure out the profit of the position is because look what I've written in red. To find the value of C here, we must first determine what the value of C is at these two outcomes, then find delta that makes the payoff on the upside equal to the payoff on the downside. If you included the unknown variable in as one of the conditions for equality, you could never solve it. So we cannot include profit in, we must only include payoff. So we have the two payoffs. If we got to pay off the loan, in a no arbitrage situation, the payoff would exactly equal the loan. Remember now, for arbitrage, we're going to borrow to finance this whole first position, and after we include the cost to carry it to the end of the term, the price of the call option, or the price of the option that we're pricing, or the contract that we're pricing, must be one such that there is no profit in financing this and carrying it. There can be no profit in doing it. So, if our payoff after an up move is delta S plus minus C plus, the loan payment must be negative delta S plus plus C plus, because if you net these out, they should add to 0. Again, if our payoff is delta S minus minus C minus, just put a negative, just reverse everything here as an outflow so that when you net them out, they must equal 0. Let's see if it does. Delta S plus minus delta S plus minus C plus C plus equals 0. That's how we know. Once these equal 0, great, we're all set. There can be no arbitrage because the payoff equals the loan. So that the no arbitrage price for C must be this formula. C minus delta S minus the present value of negative delta S plus C plus. Here's the loan payment here, right? So isolating for C, if you just isolate for C, we have delta S plus the present value of payoff plus or payoff minus. These are our payoffs. That's the loan amount we're paying off. Now, there's where I'm not happy with all the negative signs, because it makes it hard to, as I'm explaining it, you're probably going, but I'm confused. Well, you got to keep in mind here, What's in brackets here is the loan payment we have to make, not the payoff. So now keep in mind, when we have to interpret this later on, you're saying, but now hang on a second, since that's a negative, that means we're paying back a loan, we must have sold something, we must have had a positive. And this is a positive, which is offsetting our loan, so it must have been a negative. That's why I don't like all these pluses and minuses. I'm not going to carry this on much further. I just want to get you used to that. If you were reading the chapter, if you like to go back to the source text and read it, keep in mind you got to keep all those pluses and minuses straight. So all we have to do now is solve for C. And what have we really done here? This plus C minus delta S, what is this over here? Just so that we're clear. This over here is what our initial position cost minus this is the value of the loan we're paying off in the future discounted back to today. So that is all this is. All this is saying here is that whatever it cost you to finance this, if you carry it to the end of the term, that's what you would owe. Well, that's the same thing as taking the loan amount at the end of the term and bringing it back to here. So this present value is just doing it the other way. Remember before we looked at financing the original underlying and carrying it to the end of the term and figuring out what the price of the forward must be because of that, the cost of carry. Here we're trying to figure out what the cost of the call is in this case. Since we don't know the cost of the call, what we do know is if we have an up move or down move, we can figure out the price of the calls on a European call because it'll either be in the money or it won't. So since we know what the payoff is, we know the payoff must be equal to the loan. Since we know what the loan is, but we don't know what this is, it's easier to bring the call price, the loan price back to time zero than it is to carry the underlying forward. Because we don't know this. We're trying to solve this. So all we do now is just, this is all equal to zero, is just use algebra and you'll get this statement here. The call price must be equal to whatever it costs us to buy the underlying plus the present value of whatever loan we have in the future that we have to pay off. Because here we will know the value of the call option. So we will know this. This will be a known amount. We will know the discount rate. We will know the price of the stock. If you solve for all that, we'll finally have the price of the call, the no arbitrage price of the call. Abstractly, it can be confusing. Let me put some numbers behind this and show you what I mean, and then you'll go, oh, okay, I get it now. All right, let's have a look at this little example here. We got a stock that's $20 and we're going to buy delta units of this $20 stock, and we're going to sell a call at $21. We're going to sell the $21 call. Well, how much is the $21 call worth if we sell the $21 call? We would have to know something about, well, what's the expected future values of these stocks? And let's say that our up move is a 1.1. So that we take the 20 and multiply by 1.1. This is called a total return amount. We'll get 22. So in other words, we expect it to rise either 10% or drop 10%. So if we expect it to drop 10%, it's the same as saying 0.9. So in one period of time, we know that the stock will either be 22 or 18. It'll be 22 or 18, and of course we have delta numbers of it. We sold the call at 21, so at $22, what would be the value of the call? Remember now, we're using European options, final day execution only. Well, it would be, the value of the call would be worth $1. Now, some of you out there are probably saying, no, it would be -1 because we sold the call at 21. I'm saying the value of the call is $1. Think about the other side. What if I were long the call? The call's worth $1. I'm not saying the payoff. The payoff is -1, but the value, we'll get to payoff down here. The value of the call is worth 1. We'll subtract that 1 because it's a loss for us, but this could easily have been a long a call, and that would have been a +1. So we don't assign the negative or plus sign to the value. We will assign it to the position we took. So the call has got a value of $1. There are two parties to a contract. One will be up $1, one will be down $1, depending on what this says. But for now, the call is $1. If it's $18, a call at 21 is worth 0. It's completely out of the money. It's worth 0. Again, We don't know what we sold the call for. This is not profit. This is just the value of the position. So let's set the payoff to the upside equal to the payoff to the downside. In other words, S plus delta minus C plus. So what we're saying here is this is our payoff now. This is what we can sell the shares for minus the value of the call, because we clearly lost. We're short. The value is $1, so we lost $1. Must equal the value of the shares to the downside minus, of course, the value of the call. Here it's 0. And then just simplify. We'll bring the S over to this side, the C over to this side. We'll get S plus delta minus S minus delta equals C plus minus C minus. Keep going. Look what I got. On the last screen, I simply just gave you this. Now we've derived it. This is derived from setting these two payoffs equal to each other. So let's just substitute in. We know, what is C plus? It's $1. What is C minus? It's 0. What is S plus? 22. S minus is 18. Our delta is 1/4. So we are going to buy 1/4 of a share, 0.25 of a share at $20 and sell a call at 21. So what is our payoff on the upside? Well, $22 times, 0.25 shares. Delta, we know delta is 1/4 now. 22 times 0.25 minus the $1 that we lost. That's our payoff on the upside minus the $1 is $5.50 minus 1 will be $4.50. It better work out for the downside because we've equated them, right? What's our payoff down here? 18 times 0.25. The call is worth 0, so we can ignore it. That's $4.50. So our payoff is the same no matter which way we go. The payoff is the same no matter which way we go. So now we're in a position to calculate what this call price will be. The call price will be the value of the original position that we take minus the present value of the future payoff. Remember now, we can't carry the original position to the end of the term to figure out what the no arbitrage price would be, because the thing we're trying to figure out is the initial position, the value of the call. But at the end of the term, we know for certain what the call values will be. So for there to be no arbitrage, the payoff must equal the loan. So all we have to do is take the present value of the payoff, which is the present value of the loan, bring it back and solve for the unknown. And that's all we do. Delta is 0.25. The original price was $20. 0.25 times 20 minus, what's our payoff? $4.50. Divided by 1.06. Our R over here, 6%, divided by 1.06 is 5 minus 4.245, or 75.5 cents. So at this point in time, we would sell a call, a $21 call, for 75.5 cents. And we would hedge that out with the underlying at 20.25 or $20, 1/4 of a share. We would buy $5. We would spend $5 on that, but we would get 75.5. So we'd be borrowing $4.24.5. Carry that to the end of the term at 6%, it would grow to $4.50, right? If we knew what the call value was at first, we would be able to carry this to the end of the term, but we don't. So we go to the end of the term and say, but we do know what the values will be at the end, so let's just bring the present value of that loan back and solve for the missing factor. That's how we get the call price. Well, we've looked at a call. Let's look at the algebra here for the put. Now this is where it gets a little bit messed up, and this is where it gets really confusing later on in the text unless you get this now. So let's have a look at what I have over here, because this is, again, it's messed up just because of the way the notation is. And it's done this way, again, because it's in terms of cash flows. And for the math to work, I think that's what the focus is that the math is nice and neat in the end if you do it this way in terms of cash flows. But the interpretation requires a couple of steps. What do we have here? Remember, these are in terms of cash flow. We have a negative P. That means we must be putting money out, right? Because it's a cash flow. So if we're putting money out on a P, a put, we must be buying something. We must be buying the put. So we're long a put. Where do we benefit from a put? We benefit when the price goes down. So that means to figure out an arbitrage price, we need a hedged position to begin with. Our underlying must go up. If we benefit when the price goes down, our underlying must lose when the price goes down. So what do we have here? We have a plus sign in front of delta S. The plus sign means we must be getting money, right? The plus sign. Now this is messed up. You'll see in a second why this is messed up. The plus sign says we're getting money, which means we must be selling the stock. We must be shorting delta S. And by the way, that is exactly what we're doing. We're shorting delta S. Stay with me here now. Think about this. If the put, which we know we're long, benefits from a drop in price, and if we're short delta S, naturally we would think, well, then we must be short the stock because that's a plus sign. We would benefit if the price goes down. Wait a minute now, we do not have a hedged position. The book must be wrong, because you cannot set up an arbitrage argument unless you have a hedged position. We do not have a hedged position. So maybe that's a typo. Maybe it meant something else. Now, what I want to do is we're going to jump over everything here. Let's just jump over it all. We'll go through it, but we're going to jump over it for now, and let's just go to delta. Remember when we did delta for the call, it was delta equals C plus minus C minus over S plus minus S minus. Well, it turns out for the put, you do the same thing. P plus minus P minus over S plus minus S minus. But for the call, C plus would always be greater than C minus. The value of the call after an up move versus the value of the call after a down move, this would always be positive, so delta would always be positive. But over here, since we're talking about a put, the value of the put on the upside will be less than the value of the put on the downside, thereby making this negative. So delta is a negative number. Now, we don't write negative delta. We just say that delta is negative 0.5. So let's think about what we're doing now. We're not going to go short. This is what the plus sign is implying. We're going to go short. The plus sign means, again, I think I'm having a hard time explaining it. I hear myself explain it, and I think that sounds awful, but let me see. I'm going to change my color, and I'm going to try to explain it to you as best I can. The positive sign means it's a cash inflow. For there to be a cash inflow, we must be short. So the plus sign means we are short something. What are we short? We're short delta S. But here, delta will be negative inside. We don't say negative delta, we just say delta is negative. So we're going to be short a negative amount of shares. If you're short a negative amount of shares, it means you're long. It means we are long. So this plus actually means we're long when it gets to put, because the plus means that we shorted the underlying. How much of the underlying did we short? A negative amount of it. Do you get that? Do you see why it's such, like when you get to interpretation and you have to interpret the puts, you have to say, now hang on a second. Inside the delta is a negative, so I got to look at the sign in front of it and figure out what's going on. Now, if we buy the put and we are long the underlying, this is now a long position. If we're long the underlying, the put gains value on a price drop, but our underlying will lose value on the price drop. If the price goes up, our underlying will gain value and our put will lose value. Now we have a hedged position. Now we can figure out what it is. But you got to keep changing you got to figure out, well, that's a negative in front of a delta, which got a negative in there as well. So that's really a positive, right? It's a mess. It's just a mess. So you just I would say on this one, there's not a lot of value in understanding all of the steps. If you understand it for the call, just know that the put is the same way. This is just making the arbitrage argument. This is all you really have to know. This is the takeaway here, is when you're looking at your hedge ratio, it's the same as you did with your call ratio, except your call ratio, your delta, will be greater than 0. Here, your delta will be less than 0. That's all you really have to take away on this. So what I do is I just follow along as best I can. I get a mess with all the negative signs. What I want to do at this point when I multiply everything by -1 is I say, look, I've got a -1, I got a negative sign hidden inside this delta. Let me bring it to the outside, multiply everything through by -1, here's what I get, and I can get to this solution very rapidly. So if you're like me, where you like to actually go through every step to derive the formula, you'll find that when you get here, this is easy to get to just by following, just saying, well, okay, I'm just going to keep reversing everything as I go along. You'll get here, and then you say, well, I can't get here with the right signs. It's because inside delta is a negative sign. Break it out and get rid of it, and you'll get to that nice and easy. So note, P plus plus P minus is less than 0. Therefore, delta is less than 0. So if we're short negative delta S, we're actually long because we're short a negative amount, which would make us long. This plus sign means it's cash flow in, which means we're short delta S, so we're short a negative number of shares, so our underlying is a long position. I hope you are sort of nodding your head with me saying, that is messed up. I mean, that is messed up. The math may work out nice, but now you got to work like a son of a bitch to interpret this thing. I am not going to continue on with these hidden negative signs all over the place. I'm simply not going to do it. I'm simply going to interpret it in terms of the way a trader would think. What's my position? What's my financing? And you're going to see it's nice and simple. All right. So let's take a moment and figure out what we've done so far, because all of that notation back there and all those negative and plus signs can be rather confusing, because I'm going to show you how absolutely easy this is. All we've done, we've set up the no arbitrage argument to get to this statement right here, that the call price or the put price, whichever one, the call price is really just what is it going to cost us to buy the underlying, and that should be equal to the present value of the payoff. And this is why you have negatives and plus signs, because this inside here is the payoff. Well, the opposite is the payoff. This is the loan, since you got to pay it off. So this is the loan amount in here, which I really think you could have just left it as the payoff and used a negative sign in here instead of a plus sign, the present value of the loan. You see what I mean by all these negatives and positives? I even get confused. Inside the brackets is our loan that we have to pay off in the future. This is the present value of the outflow. So if we're adding an outflow, we're actually subtracting it, which it would have been easier just to say, hey, how much is the underlying minus whatever the present value of the payoff is? You could have just left it that way, but we didn't. Anyways, all we've done is arrive at this and show you how to get the hedge ratio, H. And in doing that, I also explained that I don't want to use H, that I am actually going to use delta. I put the H in so that you could see what it was in the book. So all we've done so far are these two things. That's all we've arrived at so far. So you no longer need to go back to that early part. Those first three screens, we're done with them now. If you can remember these two formulas, we're done. So let's look at the value of the call and the value of the put in a different way. Rather than having to go through the arbitrage argument every time to come up with the value of the call, can we arrive at the value of the call in a different way, knowing that the value of the call is a no arbitrage price, right? And we can. What we can do is pi here. Let's explain what our pi is here. This is really just going to be a probability. The probability of an up move and 1 minus the probability of an up move. So all this is there's the value of the call option on an up move multiplied by the probability of an up move plus the probability of a down move multiplied by the price of the call on a down move. This is just a weighted probability average of the outcome, and we just take the present value. So we have an expected value, right? The probability of a move up times the value plus the probability of a move down times the value, and we just take the present value of the expected value and we'll get a call price. We could do the same thing with the put. And this is how we figure out the probability of an up move and a down move, or probability of an up move. Probability of a down move is just 1 minus pi. Sometimes you'll have 1 plus r up here. Sometimes you'll have e to the rt. If it's continuous compounding, it'll be e to the rt minus d. If it's not, it'll just be 1 plus r minus d. So let's just go ahead and start solving problems with numbers instead of talking abstractly. And you'll see how absolutely straightforward this is. And then if you want to go back and review the first three screens after you've seen a bunch of examples with numbers, the first 3 screens, you'll say, okay, I see exactly what you're talking about now. Great. Here we go. Let's take a non-dividend stock, non-dividend paying stock at $100. There it is right there. S equals 100. And we're going to buy a call option, or we're going to value a call option. We don't know if we're going to buy or sell. Let's just say we want to value a call option that lasts 1 year. So C is, well, who knows? It's a European call. We don't know what the price of the call is. We know that R is 5.15%. The strike price is $100, so we have a $100 strike. We have an up move, 35. If the stock price moves up, the expected value will be 35% higher. So our U is 1.35, our D is 0.74. So in one period, what's the price of our stock? It'll be either 135 or it'll be 74. Great. That's the first thing you do. Once you draw out your tree, especially even if we're doing 2 periods, I like to start at the price of the stock, figure out all my stock prices, number 1. Then you'll start at the end of the tree. This is only 1 period. If it were 2, we would go way to the very end, but here it's 2, and we say, okay, if the stock in 1 year is 135, on a $100 call, what's the value of the call? 35. If it's 74 on a $100 call, what's the value of the call? 0. Great. Now I can figure out my delta, because to figure out the value of the call, I need my delta. So what is my delta? My delta is up here. It is C plus 35 minus C minus is 0. That's an equal sign, equals 35 minus 0 over S plus, it's 135, minus S minus, which is 74. So it'll be 35 over 61, which will give me 0.573775. So there's my hedge ratio, 0.5737705. So I know that I'm going to buy 0.5737 shares of S. 0.5737 shares of S. So what is the value of the call? Now what is this hedge ratio again? This is the ratio of the underlying I need such that the payoff is going to be identical no matter which way I go. If it's going to be identical no matter which way I go, then I can price the call, because it doesn't matter which route I take, it'll only have one price. So let's figure out the price of the call. Equals delta S. Well, I've already figured out my delta, 0.5737705. My S is 100. Plus, it's the present value, so I know I'm going to divide this by 1.0515. But what do I have on the top? And now, this is a real, I keep saying it over and over again, a real pain in the ass. Let's keep the negative signs in order, right? So we have a negative, because a negative, and then our delta, 0.5737705. Our S plus is 135, plus our C, which is 35. Keep that negative sign in there, right? And we're going to discount that by 1.0515. This is what it costs us. This is the value of the loan, so we have to add the payoff. We have to add the loan payoff, which is the same as subtracting the value of the loan. I don't know why we don't just do that. Okay, what do we get here? We will get 57 times 100, 57.37705 plus a negative 77.459016 plus the 35. So you negative plus the 35 brings this less negative. Discount it back by 1.0515. Gives us a price of 16.9975. So, given this situation, given this type of volatility, up move, down move, given 1 year, the value of the call so that there is a no arbitrage price on the call would be 16.9975. 16.9975. If it wasn't that price, if the call was more expensive or less expensive, that opens up an arbitrage opportunity. Okay, same problem. Except now, let's solve it a different way. Let's solve it a more direct way. And we're going to solve it as the present value of the future expected value of the call, the value of the call. So let's have a look at that. First thing we need is the probability of an up move. And that probability can be solved with this formula. 1 plus r. What's our r? 5.15%. So it's 1.0515. That's 1 plus r minus d. Our d is 0.74. Over 1.35. That is our u minus d, 0.74. And that will give us 0.510656. There we go. So we know that the probability of an up move at 0.510656, probability of a down move would be 1 minus that. So let's see if we can't find our C. And we should get 16.9975. Same thing we got on the last screen. We should get that by using this. So what is the probability of going up? 0.510656. What is the payoff of the call in that price? 35. What is the probability of not going up? It's 1 minus that. Now I know the payoff of the call is 0. Typically I would say, well, if it's 0, what's the point of me writing anything out? I'm multiplying it by 0. But for demonstration purposes here, 0.489344 multiplied by the 0. And of course it's present value, which means we discounted back. And lo and behold, we get 16.9975. Isn't that beautiful? Let's see if it worked for the put. Well, we don't know the price of the put. We haven't calculated the price of the put. We're going to calculate it here. And then on the next screen, I'm going to show you a different way to calculate the put if we already know the call. And they better be the same, right? So here, what do we get? We get 0.510656. It's the same thing. Notice that, except just the value of the put changes. Well, it'll be 0, right? If you have a strike of 100, the stock's at 135, you'll have a 0 value for the put here. But down here, 100 to 74, the value of the put will be 26. So plus 0.489344 times the 26. And of course, discount it back by 1.0515. You will find that you get 12. It's 12.0999 something, but I'm going to put 1210. How does that sound? I think it's 12.0998. I'm going to just go ahead and put 1210 because you can't get closer to 1210 than that. There we go. Let me show you another way to solve the price of the put or to solve the price of the call. Let's say that you know one of them. Let's say you know the price of the call, but you don't know the price of the put, or you know the price of the put and you don't know the price of the call. You can use something called put-call parity, where it's the stock price plus the value of the put is equal to the present value of the strike price plus the price of the call. And sometimes you'll get e to the RT, meaning continuous compounding. Sometimes it'll just be x over 1 plus r. So let's go ahead and see if we can solve for that. Remember, we knew the price of the call was 16.9975. We'll call it 16.998. We know S, it's 100 plus. We're trying to solve for P this time. We know the strike price was 100 divided by 1.0515. And we add the price of the call of 16.99. We'll round it off to 8. Our P at this point would be 100 divided by this is 95.1022349 plus the 16.998 minus the 100. Bring that over to this side, and we will get 1210. You get $12.10 on the price of the put. All right, now that we got that one period binomial option model out of the way, let's look at a 2-period option model. And here we're going to just do a lot of pricing out of this one. This one's really easy. I shouldn't say really easy, but listen, if you've been through fixed income, we've seen this in fixed income in a different sort of way, but we've seen this sort of lattice model, this recombining lattice model where each leg just adds one more item. So we go from 1 to 2 to 3. If we continued on, we'd have 4 outcomes, etc. So just to get some notation out of the way, you'll recall we start with a stock price and a call price. We have an up move and a down move. We signify that by S plus, C plus, and S minus, C minus. By the time we get to the second period, we're S plus plus, C plus plus. This would be S plus minus. It could also be S minus plus. Whichever path you take, you'd end up at the same value, C plus minus, and then S minus minus, C minus minus. just to keep the notation straight, is exactly what we're talking about. So when we say S++, this is what we really mean. We mean this value following two up moves. To value the call is really easy at this point in time. They're European calls, so we know that they are exercisable at this price. The value of the call is the maximum of either 0 or whatever the underlying price is, S++, minus the strike price. We can also think about it as if this is an up move, let's say it's 10% up and 10% up, U is 1.1, it would be the same as U squared times the original stock price, 1.1 times 1.1, minus the strike price. Here, it's the maximum of either the stock price, S plus minus the strike price, or U times D times S. And here, you can see where I'm going with this, right? So if we were looking for the hedge ratio that we would have here, recall when we did the one-period model, we needed a hedge ratio for how many shares of stock we were going to buy at this point. Well, now we work backwards. We're at these legs, so we're going to work backwards here. We need a hedge ratio here and a hedge ratio here. And then, once we figure out values here, we get a hedge ratio here. So the hedge ratio, delta plus, is the hedge ratio for here. Delta minus is the hedge ratio here. So it's just the adjoining legs, right? C++ minus C plus minus. So there's C++, C plus minus, divided by S++ minus S plus minus, divided by those two. And then for delta minus, it is these two call prices and these two stock prices that we're looking at. Then we can calculate the ratio here once we figure out a value for C plus and for C minus. So this is really just to introduce you to a lot of the notation that we're going to use. And let's move forward now and dig a little deeper. All right. So I don't have much on the screen here, but we have enough to solve a two-period problem. Our current stock price is $72. Our U is 1.356. Our D is 0.541. This is saying that if we do go up, the stock price will go up 35.6%. And if we do drop, it looks like we're going to drop about 45.9% on the downside. Our strike price is 75, so we have a stock price of 72, a strike of 75, and our R is 3% per annum. So let's see if we can't figure out what the $75 call would be here, because the strike is 75. So we have a call price here. What's the call worth? Given this type of volatility, and given that is the interest rate. So the first thing I like to do is the first pass I make is to figure out all my prices. So 72 times 1.356 gives me 97.632. And if I take that up to the next level, we'll go up this way, and we'll draw that out now. Up here would be 132.389, 97.632. Then we move down, would give us 52.8191. I just multiplied this by 0.541. Moving to the downside, we have 38.952. I don't have to move up. I'll get the same number. You can satisfy yourself that as you multiply 38 by 1.356, you'll get that result. And moving down one more time, we have 21.07303. There we go. Now from here, figuring out the call price is very, very easy. If my strike price is 75 and my stock price is 132, the call would have a value at this point of 57.389. Here, it would have a value of 0. A strike of 75 and a price of 52, value of 0, and a value of 0. So from there, now that I have this, I've done my last period time, I can figure out delta plus and I can figure out delta minus. So delta plus is going to be C++, 57.389 minus 0 over 132.389 minus 52.8191, and I will get 0.72124. So that would be the hedge ratio here. We're not going to do much with this hedge ratio. When we get near the end of solving problems like this, I'll spend 2 screens in interpreting what this hedge ratio would mean, exactly what it would mean, because it turns out that we can replicate an option by using the underlying and some leverage, Or we can take a position that we have and say, you know what, we got a lot of money tied up in that position. There's a cheaper way to do it with an option that gives us the same payoff. So let's look at what delta minus is, the hedge ratio down here. It is C plus minus, which is 0, minus 0 over S. I'll just put S plus minus minus S minus minus because we don't really have to spend the time writing on all the letters. We have 0. The hedge ratio is going to be 0 because to replicate a call, we do nothing. Why? Because the call has 0 value both ways. So to replicate something that pays 0, do nothing. So that's our hedge ratios. We can also figure out what our probabilities are, what our probability of an up move is, so we can figure out what the call price is here and what the call price is here. Actually, what we can do here, we can pretty much say, look, we have 2 zeros. The call price is going to be 0 here. So let's go back to our pie here. What is our rate of interest? 1.03 minus our D, 0.541 over U minus D. 1.356 minus 0.541 will give us 0.60. So let's price out a call up here. We want to price out C plus because that's where C plus belongs. And it will be, we have a probability of an up move of 0.6 times the value of the call at that point. We're right here, so it's 57.389. Plus the probability of a down move is 0.4 times 0. And that is the expected value of the option. And now we're looking for the present value of the expected value. Remember, we did this in the last learning objective where we could conceive of an option price as the present value of the expected value of the option, but to do that we need a probability, and we're dividing this by 1.03, and we will get 33.43. So our option price here is 33.43. We need the option price here and we need the option price here to get an option price here. That's why we say we work backwards. So again, I like to, once we have the stock price, it's easy to fill out all your stock prices. From there, it's easy to figure out what your calls are worth because you know the strike price. Take these two, figure out that price. Take these two, figure out this. Why did I say this was 0? Because if you figure out what the expected value of it is, 0.6 times 0 plus 0.4 times 0 will still be 0, right? There we go. So now we can move back to this point. We can figure out what our delta is at this point. Although for here, we're not really going to use delta. Notice that we didn't use these deltas at all. We will at some point, but I just want you to be aware of the order in which we calculate things. To calculate delta here, we needed a value for C up here. Remember, it's C plus minus C minus, right? So it'll be 33.43 minus 0 over the prices, which we have as 97.632 minus 38.952, and that'll give us 0.5697. Again, we'll interpret these later on. I just want you to see the order. So now we are in a position to calculate the value of a call at this point in time when the underlying is at 72 and the strike is at 75, given this type of volatility and given this interest rate. Our C will equal, what's the probability of an up move? 0.6. What's the value it will take on? 33.43. Plus, what's the probability of a down move? 1 minus 0.6 times the value it will take on, discounted back. The present value of the expected values of the options, right? 1.03 will give us 19.474. So C will be 19.474. A 2-year call option on this stock that is currently trading at 72 with a strike price of 75, given these type of up and down moves, given this volatility in the moves, should have a value today of 19.474. That is a no arbitrage price on the stock. If the call were cheaper, it would make sense to buy the call. If the call were more expensive, it would make sense to sell the call. If you buy the call, you're going to sell the underlying. If you sell the call, you're going to buy the underlying, because we did that we did a hedged position to arrive at the arbitrage price. So if it's off, you would just do the reverse of what you need to do. Remember, buy low, sell high. So if the price of the call were too low, what do you do with it? You buy it. If it's too high, what do you do with it? You sell it, which means you do the opposite with the underlying. Well, on that last example, we calculated the call prices moving backwards to finally calculate the call price at time 0. We can also calculate the call price directly if we know what the values of the calls are at the end of time period 2. If we know C++, if we know C+-, if we know C-, we don't have to calculate the intermediate steps. We can go right to step 1 to calculate it using this particular formula. So here's our scenario. The stock price at 50. We have a strike price at 50. Interest rate is 5%. U is 1.356. D is 0.744. So let's calculate what our tree looks like here. And let's move up in price. This would be 67.80. And we'll draw out the rest of our arms here. 67.80. This would go to 91.94. This would drop to 37.20. And if it rebounded, it would go to 50.44. 50.4432. And this would drop to 27.6768. To use this formula, we need C++, C++, C-, and we need alpha. So we had to figure out our prices first so that we could then figure out our call values. If it's got a strike of 50, we're at 91.94. It would be 41.94. There's C++. This C plus minus would equal 0.4432, and this would be 0. From this, we don't have to figure out the intermediate prices and then figure out this. We can go right to that final move. All we need now is pi, and that is 1.05 minus D, which is 0.744 over 1.356 minus 0.744. Bang away on your calculator. You'll get 0.5. Are we ready to go? C equals 0.5 squared multiplied by C++, 41.94, plus 2 times 0.5. 1 minus pi is again another 0.5 times C plus minus 0.4432, plus we have a C minus minus, which is 0. Normally I don't like to put them in, but I just want to show you what this looks like. 1 minus pi is 0.5 squared times 0. That's meaningless. That is the expected value at time period 2, and we discount that by 1.05, but now we're discounting it 2 periods. You have to square it, right? Watch your discount on that. We're coming back 2 periods. That'll give us 10.485 plus 0.2216 over 1.05 squared, or 9.7112. That's the value of the call. We didn't have to do the intermediate step. If we want to know the value of the put, if we were looking, well, that's the value of the $50 call, what's the value of the $50 put? We can use put call parity. The stock price plus the put is equal to the, equal to the strike price discounted back to today, 1 plus R. In this case, it's squared, plus the call value. So we'll get 50 plus P equals 50 over 1.05 squared plus 9.7112. And all we do is isolate and solve for P. P will equal 45.351473 plus 9.7112 minus our 50, 5.0626. 5.0626. And does that make sense to us that it wouldn't be the same price as the call? Well, we have the upside. If the price goes up, it goes up 35.6%, but if it goes down, it looks like it goes down 25.6%. It's not symmetrical. There's more upside volatility than downside, so the calls would probably sell at a higher premium than the puts would have, given that distribution of volatility. All right, up to now, those were European calls and European puts, or European options that we looked at. Final day expiration only. Let's move on to American style options, which is anytime exercise. And let's deal with calls first. Calls, we'll see, are just a minor thing here. Early exercise results in a loss of time value. Whenever you have a call option, it's going to be worth at least its intrinsic value. So let's say you have a call option on a stock at $50 and the stock is trading at $100. It's $50 in the money. It's worth $50, but if there's any time left to expiration, the money, if you exercised that call, you would have to pay $50 for the stock. You would have to come up with the $50. Well, that $50 could be earning interest somewhere. So you would forego the interest that it could earn, and since you could, it would obviously be in the price. The time value of that money would be in the price. You could always get more by selling the call than by exercising the call. So it never makes sense to exercise a call early on an American call. Early exercise results in a loss of time value, therefore better to sell than exercise. So there is no change in valuing a call between European and American style options. We don't have to change anything. Everything we've learned for the European style call applies for the American style call. Puts, it's not so much. Puts are a little bit different here. Early exercise results in a premium over European style options. Because you can exercise early, there are instances where the European option may not price in the entire intrinsic value. Plus, if you exercise a put, guess what? You get money. You get money, which means that you can put that money into lending, which then pays a return. So you actually make more by exercising early. So the moment that the option is worth exercising, it should be exercised, which means the option's minimum value should always be its intrinsic value. That's not always the case with the European option. Let's look at a case here. So here is 72 and a strike price of 75. Here's our R of 3%, but instead of the call, remember we did this before. We already arrived at these prices before. But instead of a call, we're now going to do a put. So if you go to this last time period here, if you have a $75 strike price on a put, it's got 0 value here. It's got 22 here, 53 here. Working backwards, you'd arrive at 8.614 here. Here you'd arrive at 33.86. Now here's the problem, right? So far everything is okay. So far everything's okay. This is the right value it should have on expiration. There's the right value there. This has a value of 8.6, but it's not in the money at all. So that's maybe the right value there. But look at this. If you've got a $75 strike, you could put it to somebody, they have to pay you $75. If the stock is selling at $38,952, the option is $33.86. You can see that that does not add up to $75. Does not add up to 75, which means if this were the price of the put, it would always be worth buying the put and immediately exercising it. Buying the put and immediately exercising it. So what have we got here? The intrinsic value of this put should be the strike price minus the stock price. That's 38.952, right? Because if you exercised it, that's exactly what you'd make. You'd make 36.048. Well, if it only costs you 33 to buy the put, and you can exercise it and quickly make 36, I think you're doing okay there, right? Versus 33. So early exercise premium must be 218. An American style option wouldn't trade for 38. It would trade for at least 36.04 on here because of the exercise price of 75. It would trade for at least its intrinsic value. Never mind time value. There will still be time value, but we're not even talking about that yet. It would trade for at least its intrinsic value. So that means that over a European style option, moving to an American, the American would have an early exercise premium of 218. So how do we deal with this in this tree? Well, we saw this in fixed income. If there was an issue about the exercise, if something could possibly be exercised or if a bond could possibly be called, we just assumed that it was. So all we would do is we would cross out, as we were working on this tree, once we got to here, we would just simply cross this out and rewrite 36.048 before we calculated this price. Let's have a look at that. So we're going to do a whole problem right from scratch here just to see how it's done. Let's say we observe a stock at 26 bucks. There's our 26 bucks right there. We're looking at an option with a strike price of $25. Our U is 1.466. Our D is 0.656. The interest rate is 2.05. Find the exercise premium of the put over the European put price, assuming a two-period model. Great. So the first thing we want to do is get all of our ups and downs. Get all our prices in there. So if we move up, we'll get to 38.116. I'm just multiplying the 26 by the U. We move up again, we get 55.87806. If we move down from this point, we'll get 25.0041. If we move down, multiplied by our D, we get 17.056. Move down one more time, 11.18874. So there's our prices. So now we can figure out what the value of the puts are right here, because the time is over, so they'll be worth their intrinsic value. We have a strike price of 25. If it's at 55, the put is obviously worth 0. Strike price of 25 at 25.001, the put is worth 0. And down here, the put will be worth 13.81126. So there's our put prices at that point, and then we just have to work backwards at this point. So we're going to need a probability of up and down moves, our P here, or our pi. What's our interest rate? 1.0205 minus D, 0.656, over U, 1.466 minus 0.656, and that gives us 0.45. So there we are. We're in a position now where we can calculate P plus and P minus. So for over here, we don't have to do anything. Why? Because we have two zeros. So we know right away that the put is going to be 0 at that point, and that makes sense because if the strike is 25, that's 38. We got to figure out the value here based on the expected value discounted back. So the expected value is going to be 0.45 times the first value plus 1 minus 0.45, 0.55 times 13.81126. Discounted back 1.0205 will give us 7.4436. 7.4436 it says. However, notice that if we take 25 minus the 17.056, we get 7.944, not 7.44. So we would then say, well, the put must be 7.944 because these two added together would equal the strike of 25. This is too low. So we wouldn't use the model-derived put price. We would just say, well, that's too low. Let's cross that out. We're not going to use that. We're going to use the intrinsic value amount. Now that we have that, we're in a position to solve P for over here. So P here will equal 0.45, 0 plus 0.55, and the new price, 7.944. And of course, we'll discount that back one period, and that will give us 4.28143. 4.28143. Now, we're being asked what the premium was at this point in time. Remember now, we changed this, so that is the price that we should get. If we hadn't changed it, if we left it at 7.4436 and then went on to calculate P at this point without considering that it's American, let's figure out what the European put price would have been here. It would have been 0.450 plus 0.55, but this time we're going to use the European price, 7.4436. Discounted back would give us 4.011739. So now we can answer the question, what is the premium? If it were an American style put, it would be 428.143. If it's a European put, it would be 4.011. So it's easy enough to see that the premium is just one minus the other, and we'll get 0.26969, roughly 27-cent premium because it's an American style put versus a European style put. All right, let's do a quick one here, adjusting for dividends. I don't really think that that you have to do it, but this will take no more than 2 or 3 minutes to go through this. I'm going to go through it rather quickly. I've seen no problems on the adjusting for dividends, so I'm going to assume that you don't have to. Here's our scenario. Our current price is $100, strike price of 95, interest rate 1%, D1 or dividends in 1 year of $3. So how do we get to the 118 over here? If we're moving up, we have 1.224. Shouldn't that be 122.4? Well, no, because remember now, when a company pays a dividend, the stock price drops. So what would be the stock price at one period of time? This is the ex-dividend price. All we do is we take the $100 that we would have here, we minus, we take the present value of the dividend, we bring the dividend back to this date, and then we increase that price by 1.224. Because remember now, if you had to borrow to buy this, you'd borrow the present value of the dividend separately from the present value of the stock, right? So you get to 118,746. That you multiply again by the 1.224 to get this price. So you just fill out all your prices. And then what we do now is we figure out what our calls are worth. Where's our strike price? Is 95. So what is a call worth over here? It is worth 50.36776. A call over here is worth 0, and a call over here is worth 0. So our pi, we're going to need that, is 1.01 minus, what's our D? 0.796 over 1.224 minus 0.796 will give us 0.50. And now we're in a position to figure out what our C plus is, what our call price is here. It'll be 0.5 times 50.3676, and 0 there. We'll just discount back 1 by 1.01. Will give us 24.934. Now here's the thing. The American style allows exercise before ex-dividend. There's the ex-dividend price. So the American style option allows us to exercise before that price, so we just have to make an adjustment for that. C is, remember, it's our maximum of either 0 or ST minus X. So it will be a maximum of 0 or 118.7644. That's the price, plus the dividend, because we can exercise before the dividend, right? Minus 95, and that will give us a value of 26.7644. 26.7644. Notice that we just don't add $3 to this price, right? That would give us to $27.93. It's 26.76 because we take whatever price there is here and say, well, we could have exercised the option just moments before it went ex-dividend. So the stock price would have been $3 higher, of course, minus the 95 to give us whatever the intrinsic value is. It would have been 26. So that is the price that we would put in, 26.7644. Here we have two calls that are 0, so there's no point. We know that the call here will be 0. And then from there, of course, you can figure out what the call would be at this period of time now that it's adjusted for dividends. We don't have to calculate it. We know how to do it. We just want to know how we handled the dividend at this point in time. And there it is right there. Okay, we're doing a really extended problem now. This will go through 5 screens. The last 2 screens, I go heavy into the interpretation. So you're going to want to stick around for that. The first 3 screens, it's just solving for this. This is easy stuff. We observe a stock at a current price of $7.35. We're looking at an $8 strike on an option. The puts and calls are 2 years long, so we're going to price out puts and calls for 2 years. We know we have a 2-period binomial model. R is 4.35%, U is 1.445, D is 0.715. The first thing we want to do is find out P and C at both T0 and T1. So we need P plus, P minus, C plus, C minus, and P and C if they are European. So it's easy enough that we can sort of figure out using, remember I said we don't really have to draw out the tree, we could just sort of figure it out this way. The option value 2 periods from now is going to be the maximum of either 0 or the stock price minus the strike price. Well, what will the stock price be? Well, if we're going up 2 legs, it's u squared, because we'll multiply 735 by 1.445 and then multiply it again by 1.445. So we can figure it out this way, which will give us 7.347. There's the call directly. There's the price of the call directdirectly, because we're assuming the $8 strike price here. This is just the price we would get anyways minus the $8. There's the price of C++. C plus minus is 0 and C minus minus is 0, so only 1 has value. If we're doing the puts, P plus plus is 0, P plus minus is 0.406, and P minus minus is 4.24. So this just saves you from doing this, right? And figuring out the stock price and then calculating the call price after by looking at the strike price. This is just a direct way to do it. All right, so we still have to calculate P and C. We've got C plus plus, C plus minus, C minus minus, and the P's. We need C plus, C minus, P plus, P minus, and then P and C. So I've just repeated what we've concluded on the last screen. We're going to need some probability to start calculating these, so let's figure out what our pi is. It is 1 point, what's our interest rate? 0.435 minus our D, which is 0.715 over U minus D, 1.445 minus 0.715 will give us 0.45. So now we're in a position to calculate P plus, P minus, C plus, and C minus. So P plus is going to be 0.45, and this is P plus plus, which is 0, plus 0.55, and this will be P plus minus 0.406, and we're going to discount that back 1.04. What is it? 1.0435. We'll get 0.214. So P plus is 0.214. P minus is going to be 0.45 times 0.406 plus 0.55 times 4.24. And we're going to discount that back 1.0435, and we will get 241. So that's P minus minus. Let's move on to C plus. Let's calculate that. 0.45 times 7.347. Then we have a 0, so let's just ignore that and discount this back. 1.0435 will give us 3.168. And C minus is going to be, well, we have 2 zeros, so we know that's simply going to be 0. Now from that, we can take C plus and C minus, P plus and P minus, and calculate C and P, or we can just use the formula that allows us to go directly, right? C equals our probability, 0.45. We know that that was squared, times, let me make sure I did this right so that you can see that's a 0.45, times 7.347, plus 2 times the probability of up, the probability of down, times the next call price, plus the probability of down, squared, times another 0. I didn't have to write it all out, but I want you to see that. Over 1.0435, but now since we're going from T2 all the way to T0, you're going to square that. We will get 1.488 over 1.0435 squared, or $1.37. We can do the same thing for P. So let's see if we can squeeze P in here. 0.45 squared times 0, plus 2 times 0.45 times 0.55 times 0.406. That's the next one. Plus 0.55 squared times 4.24. All over 1.0435 squared, of course, will give us 1.484 over 1.0435 squared gives us 1.36. 1.36. So again, you can go directly from T2 to T0, but the question is asking us for the put and call price at T0 and T1. So here's T1, C plus and C minus, P plus and P minus. And if you would have used C plus and C minus using this, the way we arrived at C plus, using the same formulation, you would have arrived at 137. And if you would have used 2.214 and 241 using the same method, you would have arrived at 136. Or you could just go direct like this. I find that once I have these, this is just easier to work with rather than writing out all of this. All of these keystrokes, every one of these requires a keystroke. That's a potential mistake. So look at all the keystrokes in my numerator. Look at how few keystrokes I have over here, especially since I have zeros here. To calculate C from this, especially if this is a 0, it's 3.168 times 0.45 divided by 1.0435. That's direct. It's as direct as you can get. So I find that this to be, if I didn't have to calculate the intermediate put and call prices, yeah, let me go right from T2 to T0. But if I got to go from T2 to T1, then T1 to T0, I already got these. It's an easy step to go back one more rather than putting all this in, because I'm telling you, it's not hard to think you hit a decimal but you didn't, or to hit 0.45 and the 5 doesn't click, and you have 0.4 squared when you're looking at when you're in an exam situation, you're hitting those keys on the calculator. It's easy to miss one. So I look at all this and I go, that's a lot of opportunity to mess up. This, not so much. I got a better probability of not messing up here. Now notice that we just use formulas and we wrote all the things down on the screen. I still prefer to use the tree. I can do it faster because once I'm doing this, I have to keep my eye on where everything is. And when I can visually see the branches of the tree, when I can visually see it, when I do it on the screen, I visually see it. To me, it's very simple to work back. So if you're like me and you like that tree, you don't have to do it this way. Just do it with the tree. All right, our next question is calculate delta at T1 and T2. Actually, sorry, that is wrong. T1 and T0. Let me change that on the fly. Calculate our deltas. All right, well, here's our C++, C minus, C minus minus, and again, our puts for that period of time. To calculate our hedge ratios, we need all that. Plus, we're also going to need S++, which is going to be 735 times 1.445 squared. That'll give us 15.347. We're going to need S plus minus, which is 7.35. 1.445 times 0.715. That'll give us 7.594. And S minus minus 735.715 squared gives us 3.758. There we go. So now we're ready to go. Let's calculate our hedge H plus for the call. So that's H plus. We need H. H plus is at time period 1. The sub C means it's for a call. We know that that is C plus plus minus C plus minus over S plus plus minus S plus minus. And we have all of our numbers up here, so we just plug it in. 7.347 minus 0 over 15.347 minus 7.594 gives us 0.9476. So that's H plus C. H minus C, the hedge ratio at the bottom part of the tree. C plus minus minus C minus minus. S plus minus minus S minus minus gives us 0, because these are both 0, over, I'm not even going to write out the numbers, I'm just going to write this out because it's 0 anyways, equals 0. There we go. Now we can calculate the hedge ratio plus for the put in that situation, which we know is P plus plus minus P plus minus. S plus plus minus S plus minus. Let's go. 0 minus 0.406 over 15.347 minus 7.594 gives us negative 0.0523. So when we use delta, we don't actually say that we have negative delta. We will say delta equals negative this. So remember that wrapped up inside our delta is a negative number. Now I'm using H here as the book uses H to say the hedge ratio, but it is delta that I'm calculating. I like to call it delta. The book likes to call it H. I'm showing you that, using it interchangeably, but when you see delta on a put, right away you have to say there is a negative sign inside there that's not showing up here. You always have to remember there's that negative sign in there, right? H minus P is P plus minus minus P minus minus over S plus minus minus S minus minus. And what is that going to give us? 0.406 minus 4.24 over 7.594 minus 3.758. This should come as no surprise, by the way, negative 1. It's going to come as negative 1. Why? Because both puts have value. Both puts have value. So if they pay off, if there's a value for a put in both directions, it's 1. It'll always just be 1. It can never be greater than 1. It'll always be 1 or something less than 1. So this should come as no surprise that it's 1, but it's a negative 1. It's a negative 1. All right, let's finish that question off. We needed the hedge ratio at time period 0. We just did it all for T1. We need T0. So H for the call is C plus minus C minus, S plus minus S minus. We had to calculate C plus and C minus before we got there. We get 0.5905, and for the puts, you'll get to negative 0.40929. All right, nice messy screen on here, right? But it's really not that bad. Here's what I've done. Here's the stock price, 735, and here's 2 up moves. Here's an up and a down. Here's a down, 2 downs. All I've done is I put the stock price in here. This is for puts. So these are all the put prices that we already calculated. I got them circled in red at each of the stages. And in purple, I've put all of the hedge ratios that we calculated. That's why I like doing the tree, because as I calculate it, I can put it in and I can see if I'm missing nodes on anything, right? I should have a stock price and a call and an option price at each node. I should have a hedge ratio at each of these connecting nodes at time period 0 and at T1. There's no hedge ratios here unless we had a third time period. Then each of these would have a hedge ratio as well. So I'm all done. So let's calculate these. And what I've done in green is I put an A beside this, a B implying all of this, and a C implying all of this to tell you what all this stuff means. So let's say A. Let's say that we buy a put for 0.214. So we buy a put. It is identical. The payoff on this position is identical to selling 0.05237 shares at 10.6207. That's the price. For 0.5562 and lending 0.77022. Now you may think, hang on a second, that's where I lose it. What do you mean lending that? Well, listen. Let's say we just bought a put. Think about it in your mind. That's all you're going to do is buy a put. So you're going to buy a put and it gives you a certain exposure. But it's going to cost you some money. It's going to cost you 0.214. So you reach in your pocket, you put 0.214 on the table. What we want to do is we want to take a position in the underlying that puts you in the same position. So to put you in the same position, you must reach in your pocket and take out 0.214. So let's say you reach in your pocket, you put 0.214 on the table. Great. Okay, so there's the cost. We put you in the same cost situation. We need to put you in the same payoff situation, and that means taking a position of 0.05237, a short position of that much, in the shares, right? A short position. If you buy a put, you make money on the way down. If we're trying to replicate the put with the underlying, you must short the shares to make money on the way down. You must do in the shares what the put is doing for you, and we're going to pay the same price because we want ourselves in the same position. So that's why we're going to pay 0.214 anyway. So we put 0.214 on the table. But if we sell these shares, we're going to get 0.5562. Well, what we're going to do is we're going to take that along with the 0.214 we put on the table, That'll add up to 0.77022, and we're going to lend that at whatever the risk-free rate is, and we're going to make some money on that. We're going to lend that. So now we are in the same position as if we had bought the put. We're in the same position. We just simply financed a loan, we lended 0.77022, partly financed by the sale of shares. In this scenario, we're out 0.214 and we benefit from a decrease in price. In this scenario, we're out 0.214 and we decrease from a drop in price. So you just trade off. It's one versus the other, right? Look at B. How can we replicate B? You can buy a put for $2.41, or to achieve the same out-of-pocket expense and the same exposure, you can sell one share, because that's your hedge ratio, sell one share for 5.2553 and lend 7.6653. That's these two numbers added together. Now, I may be off from the example in the book because I didn't round off. I didn't round off any of my calculator numbers to get these numbers. So I'll be off by a couple of digits at the end here, but I've done the same thing. So what have we done here? If I bought a put, I part with $2.41. That's what that option cost me. In return, I profit when the stock falls. If I short one share, I profit when the stock falls. So let's say I'm still going to part with $2.41. Great, I part with $2.41, but the short sale provides me with $5.25. So I will add that to the $2.41 I part and lend 7.6653. I'm just replicating if somebody bought the put and I did this, we would be in the same position. We would both be out $2.41. We would both benefit from a downside move in the price of the stock. And again, I think you can figure out what's going on at C. We can buy a put for $1.36, or we can short 0.40929 shares at $7.35. That would generate 3.0083 in cash. We would add the $1.36 to it. We would lend 4.36. So if somebody bought a put, they spent $1.36 and benefit from a downside movement. If we shorted one share and lent out 4.36, the net result is we part with $1.36. Because this 3 wasn't ours, we're just adding $1.36 of our own money to it. We part with $1.36 and benefit from downside movement in the shares. So, what's the lesson here? The lesson is that you can replicate any option with the underlying and a combination of lending and borrowing, or you can take positions you have in stocks and you can say, you know what, we've got this stock on this much margin, or we're short these shares, and you could say we can simplify by getting rid of all of these big expensive positions and taking an option instead. So the point here is that the option and the underlying position, when we set it up this way, are interchangeable. They mean the exact same thing. All right, let's have a look at the calls. Same thing here that I've done. Here are all the prices, but in red, instead of having the put prices, I've now put the call prices, and in purple, of course, or pink, whatever color you see there, I've got the hedge ratio. So I put A, B, and C. So let's interpret what A here means. We can buy a call at $3.16.83, or the identical thing is to buy 0.9476 shares at 10.6207. That'll cost us 10.06. However, the call was cheaper at 3.16, right? So we'll borrow the difference. We borrow 6.8958. So think about that. How much are we out of pocket? We're out of pocket 3.1683. So we can buy the call for 3.1683, or we could buy a certain number of shares and partially finance that with borrowing. Again, the same thing applies to B, which our hedge ratio here is 0. The call is 0. So if we buy a call for 0, it's the same as doing nothing. Buy 0 shares for 0, borrow and lend nothing. It's juvenile to even think about that, really. Number C, what do we got? We could buy a call for $1.37, or we can short 0.5905 shares at $7.35, which generates $4.34. And to finance that $4.34, we'll borrow $2.97, which leaves us out of pocket the same price as the call, $1.37. All right, these next two learning objectives deal with interest rate options. But, we've seen a lot of this in fixed income. We have seen this, and not just a two-stage, but we've seen how to extend it into more stages than two. So we don't really have to spend a lot of time here. It follows the same process that we followed before with one slight change. So I'll show you that change. So in orange, this is the path of the interest rates. We're not given a U or a D. We're sort of just given this and saying, okay, well, look, here's this. And then we're shown where the small distinction is. But these are the interest rates. Below is the discount factor for each one. So it's 1 divided by whatever it is. This is 1 divided by that, of course, squared, because it's 2 periods. That's 1 period, etc. Right? So to figure out our C++, C plus minus, C minus minus, notice that the strike price is 3.25. Here we're 3.97. So it's 0.72 expressed as a decimal. This is expressed as a percentage, but expressed as a decimal will be 0.007206. And did the same thing over here, 0.000042. That's a 0. This is we have to figure this one out. This is the one we're going to figure out. We just did the 3 C's. And then the P's, this would be 0. If we're talking about 325, this would be 0 because it's over 325, and this would be 0.009907. So let's go ahead and solve for the value here, the C plus, the C minus, the P plus, and the P minus, so that we could figure out C. And we're told that our probability, our risk-neutral probability up and down, 0.5 on the way, 0.5 of an up move. So we got 0.5 of a down move as well. So it would be 0.5 times the rate, the call price on the upside, 0.007206 plus 0.5. And this time we do have a value on the bottom, 0.000042. And of course that is divided by the discount rate, here we can multiply by the discount rate or divide it by 1.039084. That'll give us 0.003488. For the next one, let me just change color here. We're going to use these two legs right here. So we have 0.5 of, what is our C plus minus? 0.000042. And the C minus minus, the value down here is 0, divided by, and we're going to use this rate now. Now notice, this is the thing that the reading wanted to point out, is previously we had one rate. When we were doing equities, we had one rate, and we would discount C plus, C minus, P plus, P minus by the same rate. But here, because we're pricing out the call back here, this is the rate at the beginning of the term, this is the rate we would discount it at. Whereas down here, this is the rate we would discount it at. So the denominator changes. Depending on what leg we're on, the denominator would change. So for P plus, that would put us up here. We have to figure out these two. What's our two values? Our two values are 0. We don't really have to go any further. We could just put 0 and be done with it. But it would have been 0 divided by 1.039084. Just to be clear, just to show you what the denominator would be. This one down here would be 0.5 times 0 plus 0.5 times 0.009907. And we're going to use this rate down here, 1.026034, and that will give us 0.004828 for the value of P minus. So there we go. I'm going to take it, we're going to do one step further and calculate C and P just to show you what happens when we get down to this end. But notice that wherever we happen to be, wherever we're calculating the C or the P value for, we use the rate at that particular node. Alright, so I put in the values here that we just calculated, C plus, C minus, P plus, P minus. Now we're going to calculate C and P directly here. Notice that we cannot go directly from the final leg all the way to the first leg as we had done before, simply because we have different rates at each node. So we actually have to take it step by step to incorporate those rates. So our C at this point would be 0.5 times C plus, and our C plus is 0.003488 plus 0.5 times our C minus, and we do have a value for C minus, although it's almost non-existent there. And that will be over this rate at this point, the rate at the node, 1.030454, and that'll give us 0.00170216. And our P is going to be our P plus. Do we have a P plus? It's 0.5 times 0 plus 0.5 times 0.004828 over the rate at that node, 1.030454, and that'll give us 0.00234266. That's it. It's fairly straightforward. You just follow what we did with equities. However, the one thing is you cannot go from the final leg to the first leg with the closed form formula that we used before. And as you go through each node, you have to use the interest rate at that particular node because this is a path of interest rates. Okay, well, now we want to move from discrete time to continuous time, which means we need another model. And of course, the Black-Scholes model, or sorry, the Black-Scholes-Merton model is standing right there in front of us. We got to get through it. So let's start with one of the basic assumptions, and I shouldn't even call it a basic assumption so much as that it's an observation, and this observation allows us to use a continuous time model to find the price of an option. The percentage changes in stock prices in a short period of time are approximately normally distributed. And number two, changes in successive time periods are independent. Those two things combined result in a stock price that is itself log-normally distributed. And this is the problem, is that how do you model the stock price? Because it is bounded by zero, so it cannot be negative. Theoretically, anything can, but practically it cannot be zero. So that the stock price at any point in time, at any future point in time, the natural log of that stock price will be normally distributed. Not the stock price itself. The stock price has a log normal distribution, so the natural log of the log normal distribution will be normal. So this will have a normal distribution, which means that the mean is going to be the natural log of the original price of the stock that we, or the asset that we originally saw, plus, and this over here, well, what are we doing here? This is the expected value of the underlying asset, and we're going to assume it's S naught. This is the variance, 1/2 of the variance squared, so it's just a drift component scaled for time because the variance and the mean are expressed in annual terms. This is the expected return per year. This is the expected variance per year. These are expressed in annual terms, so we scale it by t. If t is 1, then nothing changes here. And with a standard deviation of sigma, again, multiplied by the square root of t because it's scaled for time. So let's just do a really quick example to see how we move back and forth from returns to the stock price. Let's take an observation here. Let's say that at some point in time, t equals 0, we observe a stock price of $40. Expected return of 16% per annum, volatility of 20% per annum. This, let's say we got that from historical observations and we expect really nothing to change on this. What is the probability distribution of ST in 6 months, t being 6 months or some future time period, but what's the probability of the stock price? The probability distribution of the stock price. And let's say we want to have we can do a 95% confidence interval to describe that distribution. We know that the natural log of the future stock price is distributed normally with a mean as follows and a standard deviation. So we can solve for mean and standard deviation. We know what these variables are now, so we solve for that, we get this. Well, what do we do with this? We want the probability distribution of ST, not the natural log of ST. Well, follow along here. if we're doing a 95% confidence interval, we know we just take our variable and we bookend it with our mean minus a z-value for 95% times the standard deviation, and the mean plus the z-value times the standard deviation. That's just a confidence interval. Well, if this is the natural log of st and we want st, it implies that we simply just raise each of these terms as a power term to e. Because if you take the natural log of both sides, if you take the natural log of this, you will get, if you do this, you will get this. And if you take the natural log of this side, you will get this. And then, of course, natural log of st is this. So working backwards, you can see how you get there. Well, this is easily solved with a calculator. There we go. So we can get a 95% confidence interval on the stock price. It's 32.55 to 56.56. So given those last two screens, that nice little intro, we can go right to the assumptions. So let's look at our assumptions. Stock prices are log normally distributed. Do we get that now? Can we actually see it in our head as opposed to remember it? No transaction costs. Now we assume, we always assume transaction costs away, even though there are transaction costs. And we're going to see with a continuous option valuation model, these transaction costs can actually be a problem. But we assume it away. No arbitrage opportunities. That means that the price we see is a no arbitrage price. Trading is continuous. And that's not always true. Because a stock that closes at 4 p.m. can have news that comes out overnight, so that at 9:30 a.m. You may have something like this, where that was the close price and it gaps up. So that's not continuous. So it's not. That's a bit of a problem. This is more exact for currencies. And for futures contracts, because trading in currencies and futures is to some degree almost continuous. If you use something called Globex for futures, you can trade futures contracts all through the night. Borrowing and lending at the risk-free rate, and the risk-free rate is constant, and that's really over a short period of time. We're looking at European-style options. A constant and known volatility of the underlying, so you're looking at historical returns to calculate what volatility is, which has a bit of a problem in forward-looking volatility, but we'll look at something at the end of the reading called implied volatility, where it can deviate from historical volatility if the market starts to price in that implied volatility. How do we know they're pricing it in? Because the option price deviates from what historical volatility would say. So rather than the market saying, aha, there's an arbitrage opportunity here, it says the implied volatility must be this. And then you make a bet on volatility, whether it's too high or too low. A liquid underlying, and a divisible underlying. And this is more just to make a theoretical argument. It doesn't necessarily have to be divisible out there, just to make the argument. Short selling with full use of proceeds. And geometric Brownian motion describes price movements. In other words, continuous and smooth, number one. Number two, each next move is independent of the previous move. And we made a point of mentioning that 2 screens ago. So I think having gone through those last 2 screens and having sort of a high-level view of what was going on, these assumptions, you can almost say, yeah, I could have probably listed some of these assumptions without even seeing the assumptions, just based on the path we took to get here. All right, let's have a look at the model here, and we're not going to get into the details of how we derive this model and what everything means. I'm going to look at it from a very high level. So because we don't really need to at this level, really, we just need to interpret the output. Understand what the inputs are and interpret the output. How the model gets to where it is, or how it became what it is not necessary for where we are. If you want to know it, then go ahead and pursue it, but you don't need it here. And it's an extra 4 or 5 days of fighting with this model to really intuitively understand what's going on. The majority of it is easy, except there's one part that's a little bit tricky where you have to think, well, why is it doing that now? And so I'll try to get you through this just really understanding what you need to know for level 2, but not so much that we become experts at this model. Here's how we price out a call. Here's how we price out a put. So let's just ignore all the ND1, ND2 terms for now. And strip them out. What do we have? In essence, the call is the present value. This is we're discounting back to today. S is observed in today's dollars. X is the strike price at some future time, discounted back to today. This is just the payoff, the expected payoff. So the call is just the present value of the expected payoff. The put also is the present value of the expected payoff. So at the heart of it, the call is what it should be. The put is what logic would say, well, that makes sense. The price you would pay for something today is the present value of its expected payoff in the future. But this is a stock price with a random walk component. So we don't know where it's going to go. So we can't say, well, the call is $3. Well, it's $3 if the price in the future were this. But what is it today, being that we don't know what the price in the future is going to be? That's where we introduce these distributions. And this gives us some probability measure of what they'll be in the future. So let's look at what ND2 is. It's applied to the strike price. This is the probability that X, that the strike, the call itself will finish in the money. This is capturing the probability that X will finish in the money. If it doesn't finish in the money, then the call is worth 0 in the future. This captures the probability that it finishes in the money. ND1's a little more complicated. It's a conditional probability. It is a probability distribution of the stock price given that the stock price is above the strike price. That's all that is, so that we can get some probability of what the value of the stock would be if it was over the stock price, minus the expected value of whatever the exercise price would be. And well, this is the present value of the exercise price multiplied by the probability that we'd actually have to pay it. So that's all that is capturing. And D1 and D2 are captured by these terms over here. D2 is sort of just a simplification. It's just D1 minus a term. That if you wrote out D2 and you added this term, you would get D1. D1 doesn't help us really see what's going on. So let me just see if I can just do it briefly and see if you can recognize what this looks like. D2 is capturing this. It is saying some expected value minus, well, let me get rid of that. Some expected value minus what the mean is divided by some standard deviation. So if it's an observed value minus the average value over standard deviation, what are we getting here? We're getting a z-score. And D2 is a z-score in here that tells us what the area under the curve would be. And that gives us the probability that X would be in the money. Very high level. Again, very high level. So an N, D1 or ND2, this is the standard normal cumulative distribution. The standard normal cumulative distribution. So it's the CDF. This down here is what we call a PDF, the probability distribution function. So at each point there's a certain probability, and that's the distribution of those probabilities. This would be the cumulative distribution function. So at this point in time, we know that this should be 50%, right? And this just adds up what the area under the curve is at any given point in time. That's what ND1 and ND2 are capturing. Since the BSM is a continuous time model, R here is continuously compounded rate. In the binomial model, we used for the discount rate 1 plus R. Here we're using e to the RT because this is a continuous time model. And N bracket X, whatever, ND1, ND2 represents risk-neutral probabilities. And the rate, R, that we're using is the risk-free rate. So for example, if we get a z-value here of negative 1.645, and we put it through the cumulative distribution, what should we get? Well, at negative 1.645, we know we have 5% left in the tail. Our ND2 should spit out for us 0.05. Well, ND2, ND1, if we had ND1, if we were looking for any area under the curve at negative 1.645, if that was the value inside this function, we would return 5%. You should remember this from level 1 statistics. You should remember the z-score from level 1 statistics. So the only complication here is ND1. We have to remember that that is a conditional probability. This is just the probability. This is the expected value, the present value of the strike price weighted by the probability that it'll be in the money. This is the current stock price multiplied by the conditional probability, number one, that S is above, or that ST at some future point will be above the strike price. That's ND1 will cause you more difficulty than anything else. The rest is pretty straightforward. So these next few statements here, I don't find that they're so unique to BSM. This is, I mean, you don't even need Black-Scholes-Merton to make these statements or to conceive of a call as being a portfolio of a stock and a bond. We did this before with the two-period binomial model where we said, listen, we're going to buy the stock and we're going to borrow money. The only thing we didn't say when we were borrowing money is, well, how are we going to borrow money? Here, we're actually saying, well, we're going to issue a zero coupon bond. Okay, well, that's just the form of how we're borrowing money. So we were conceiving of a call as being made up of a portfolio of the underlying stock plus some bond, whether we were issuing a bond to borrow money or short selling stock to buy a zero coupon bond. We were doing something. Here, it just makes it explicit saying, you need to be able to replicate the call to be able to price the call. That's all we're doing here is saying, to price this call, let's replicate it with the underlying. And if we can replicate the payoff of the call with the underlying, then the cost of the underlying must be the cost of the call. Because by the law of one price, two assets that have the same payoff must have the same price. So the Black-Scholes-Merton model can be seen as having two components. So for calls and puts both have the same components, a stock component and a bond component. The stock component for the call is the stock price times its distribution. And for the bond component, e to the negative RTX. This is the way the CFA text writes it, e to the negative RTX. I prefer to write it as x e to the negative RT. So sometimes I'll write it this way, sometimes I'll write it this way. Keep in mind, this is just the same thing. Most textbooks I've seen that I've used write it this way as opposed to this way. There we go. And of course, times ND2. So the call price is the stock component minus the bond component. The price of the stock component minus the price of the bond component. The stock component, again, S is denoted by this term here, and B is denoted by this term. The goal is to replicate option payoffs with stocks and zero coupon bonds. And again, if you can replicate the payoff of the call with the stock and the zero coupon bonds, you clearly know how much this costs. That must be the cost of the call based on the law of one price. For puts, the stock component, notice it changes to negative D1. And that makes a lot of sense, because if you have ND1 here and negative D1 here, let's say that you have a call and a put. Let's say that you buy a call and you buy a put. Which one can pay off? Well, only one of them can pay off. You can only be right on one of them. So if you have a call, and if you buy a call and you buy a put, you're going to be right on one of them. You don't know which one, you're going to be right on one of them. So the distribution under the curve that represents the call and the put together must be 100%. So whatever the value, whatever the area under the curve is for D1 and D1 for the call, you simply just reverse it for the put and negative D1, because these two must add up to the total area under the curve. Because if you have the call and the put at the same strike, no matter which way that price moves, one of them will move up, one of them will move down. So no matter which way you go, one of them is going to work out, right? The bond component is simply, again, if this is D2 and D2, this is N negative D2. It's just, we're just covering 100% of the area under the curve. Think about it this way. Let's say that you do a box trade. A box trade means you're long one share of a stock and you're also short one share of the stock. There is no probability distribution associated with your returns. You've got everything covered. You can say, well, your return is 0, but you've got 100% of the returns covered. Whatever you make on one side, you lose on the other side. You've got everything covered. Well, that's all this is. The entire area under the curve is covered when you go from a stock to a put, it's just the opposite of what it will be. We'll see that a little bit later, so I won't harp on it now. I just want you to be aware that by putting negative signs in front of here, if this is a call, to get a put, all you got to do is put a negative sign in front of these things and you have the value for the put. That's how easy it is to go from a call to a put. So these are long calls. So for long puts, you just throw a negative sign inside the brackets. And we're going to see what happens when we go from short calls and short puts. What happens where the negative signs happen there, all right? And of course, this is the B and the S, the terminology for the bond and the stock. And the put is the bond component minus the stock component. So whatever the cost of putting this together must be the cost of the put. So there we go. The cost of the stock and the bond portfolio must equal the value of the call or the put, depending on what direction you're going on the stock, long or short. And again, the hedge you're going to use with the bond so let's look at calls. Calls here, NS times S plus NB times B. Well, what is NS? NS is the distribution. ND1, this is telling us how much stock we're going to need to buy of S. This is telling us what percentage of a zero coupon bond we need to buy. Now the book says how many shares of a zero coupon bond we need to buy. I don't like saying that because a coupon bond or zero coupon bond, any bond, you don't really buy shares of. You can buy part of the bond. You can say that I'm going to invest this much into a zero coupon bond that matures at this value. But to say I buy shares in it, it's just sloppy writing and it's confusing. I don't like to say that. So what are we saying here with the call? We're saying that we're going to buy stock. How much stock? NS stock. Whatever the value we get out of the probability distribution or the Z table, the normal table, will tell us how many shares of stock we buy. We'll get something like a 0.63 or 0.72. We'll interpret all that shortly. But in the end, we're saying that we're going to buy stock and we're going to sell bonds. So we have a negative in front of that because we're going to go short. So if we buy so many shares of stock and we sell so much of a bond, we're selling the bond to finance the purchase of the stock, we can replicate the payoff of a long call. Now, it's not so much that the cost of putting the portfolio together gives us the cost of the call. We can put this together for zero money. We could say, look, we got to buy so many shares of a particular stock. It's going to cost us this much. Sell a bond that does it for us, right? And we can come up with zero. But here's the deal. As the stock price rises, this is continuous now, not discrete. We don't do it at time points. This is continuous. So as S rises, ND1 will also rise. The value of D1 will also rise, so this probability will rise. As S drops, ND1 drops. Therefore, you must hedge by buying more stock in rising markets and sell stock in falling markets. The cumulative losses of buying, as the stock is going up, you got to buy. As it's going down, you have to sell. Those cumulative losses of buying high and selling low, that equals the call. That's the call price. So by the law of one price, the total cost of the stock and bond portfolio is the cost of the option. So rather than all of this dynamic hedging that you have to keep doing as ND1 rises and as prices rise and as prices drop, you got to buy on the way up, sell on the way down. That's just a losing game. Well, all of those little losses add up to what you could have just bought the call to begin with. Or let me say that differently. All of those gains and losses add up to the price of a call because that's what you're going to lose anyways. So it's not that it adds up to the price of the call. It adds up to a total that then becomes the price of the call because that's what you would lose anyways. Let's get some clarity with some numbers. Things always look better with numbers, right? We observe a stock price today selling at 100. We're looking at the $100 strike on a call. Risk-free rate is 5%. We're going to look at a 1-year term to expiration on the call, and the volatility on the underlying is 30%. To get to our call price and our put price, we know we need a value for D1 and a value for D2 so that we can calculate probabilities. So D1, we've already had the formula for D1. we just substitute in. We have a stock price of 100 and a strike price of 100. This is an at-the-money call. An at-the-money call will be 1. S over X will always be 1. So the stock really doesn't have to go anywhere. That's what this is saying, is that you don't need any return. You don't need any return on the stock to get to that strike price. So the natural log of 1 is going to be 0. That just goes to 0 to show that it's not going to affect anything. If it's an at-the-money call, we don't have to worry about getting there. We're already there. So we just have our final term, and we will get 0.3167. We're just substituting in and solving. 0.3167 for D2, it's 0.3167 minus whatever our denominator here was. It's the same thing, 0.0167. And if we look up the area under the curve for the cumulative function for n at 0.3167, we'll get 0.624. And at 0.0167, we'll get 0.507. Now, remember I said that ND2, you can think of ND2 as the probability that the call option expires in the money. Theoretically, yeah, that's what you would say. I've mentioned this in other places. I'm not a fan of in the real world, of actually saying that that's what that is. I'm not a fan of saying that that's what that is. Why am I not a fan of that? Well, because in getting to this probability, we used a historical measure of volatility. And what we're going to see at the end of this reading is that volatility in this model, volatility is the one variable we cannot observe. And we need future volatility, not historical volatility. And the market will price in the volatility it anticipates or that it feels. Hence, that probability may not actually be the right probability, because this output is a function of the input, and the input is a volatility, and if the market can price in future expected volatility, that's a subjective component. That's why I don't really like to say, oh, well, then that's the probability, objectively speaking. No, it's not. Again, you're going to find some people that say, yeah, that's the probability that the call finishes in the money in the real world, and you'll get some that say, well, you can't really use that as a probability anymore, because now we're talking about implied volatility versus actual observed historical volatility. So I just want to get that out of the way. Anyways, let's just stick with the math, right? These are the outputs that we would get for ND1 and ND2. Notice ND1 and ND negative 1 better add up to 1 because this is just the negative of whatever this number is. So we can get to this value by just taking 1 minus whatever that is. They must add up to 1. Same with ND2 and N negative D2 must add up to 1 because the area under the curve is just 1. If you want to think about it this way, let's take a call and a put at the same strike price. A call and a put at the same strike price, and I like to draw it out like that, and let's say that's the strike price. Where does the call have value? Up here. Where does the put have value? Down here. And that's the whole range of prices. It's either the call or the put. So if you're looking at the area under a curve, it's either going to be in favor of the call or in favor of the put. It can only add up to 1. So that's why these, when you go to the negative, it just adds up to 1. And again, this is the probability that the put expires in the money. If this is the probability that the call expires in the money, if we got a 50.7% probability that the call expires in the money, 50.7%, well, you can't have more than 1, so this must be a 49.3% probability. It has to be, because if there's a 50.7% chance that the call finishes in the money, that implies a 49.3% chance it finishes out of the money. Well, to finish out of the money would put the put in the money. Do you get that? All right, so let's calculate the call price. And again, all we're doing is substituting in. And again, for the put price, we just substitute in. We get 14.17 and 9.29. Yeah, that's not very interesting in itself. That is not interesting. It's the terms here that become interesting, because later on we're going to talk about delta hedging and gamma. Well, I don't know so much that you would call it gamma hedging as gamma management, but we'll call it delta hedging for now. So what is this saying? For the underlying, how do we replicate the call? So the call is $14.17 to buy. We don't have to buy the call. We can replicate that call by doing this. We can buy 62.4 shares. Let's say it's 100 shares. We can buy 62.4 shares, and finance it by selling 50.7% of some zero coupon bond that matures at 100. We'll sell 50.7 of it today to finance that. The difference would be the cost. What are we out? Well, the cost of the call. Same with the put. This is telling us that we buy bonds and we short shares. So again, the call, we're selling bonds, which means we're borrowing money. We're selling bonds, so we're going to have to pay that back at some point at the risk-free rate. So we're selling bonds and using the proceeds to buy shares, or we could simply buy the call. And the argument that we're making here is that we should be indifferent between the two because no arbitrage exists. We should be indifferent between the two. Now, when we get to implied volatility later on, we're simply going to have to make the assumption that, well, listen, if it looks like there's an arbitrage opportunity, there isn't. The only reason it looks like there's an arbitrage opportunity is because the expected future volatility is different than what we think. So we just have to take it on faith that the call option is a no arbitrage price and say, well, it's a no arbitrage price. It must be volatility, our estimate of volatility that's off. And we'll see our last learning objective takes that. So what we do is we look at the call at 14.17 and say, well, fine, I can buy the call or I could just do this. And same with here. I can buy the put for 9.29 or I could just do this. I can buy bonds. I can short the shares, take the proceeds from shorting the shares, short it in this ratio. Let's say I'm doing 100 shares. I would short 37.6 shares. I would short that. Use the proceeds to buy bonds. In this value, 0.493 or 49.3% of whatever this value would be. That, look up here, this keyword interpret, that's what you need to do. Is to say, well, if I have a position that looks like this, what does that equal in terms of calls? And if I have a position that looks like this, what does that equal in terms of puts? Or if you have a portfolio of options and you say, okay, well, I have a bunch of calls and a bunch of puts, what does that equal in terms of the underlying? Now, this becomes important later on when we have a portfolio of assets and we need to hedge some type of risk. And we say, well, we need to hedge some type of risk. How would I add calls and puts in such a way that it hedges that risk? This is what this begins to get us to. All right, so here we go. Let's buy a call. Let's sell a call. Let's buy a put. Let's sell a put. And I'm going to show you how easy this is. To do. Let's think about it in terms of payoff. When you buy a call, remember, what is the value of the call? It is the maximum of. Remember, our call is either the maximum of 0 or ST minus X. So that's all I'm doing here. Is I'm ignoring just the 0 and I'm putting how you would write the payoff to the call. ST minus X, here it would be negative ST plus X. If we sell a call, it is negative ST plus X. And you can work this out yourself to see that that actually is the payoff, because now we're selling a call. We certainly don't want the price to go up, right? Here, buying a put, it's the strike price minus the final price. And here, if we sell a put, it's negative X plus ST. So this is just the payoff that you would write in one of these little payoff sort of formulas. So from that, we can then do a replication strategy. If we have ST, we must be buying ND1 shares. Here we have a negative sign in front of this, so we're selling. Here we have a negative sign, so we know we're going to sell. We don't have to put anything down right now. All we have to do is just say, no, this is a positive sign, so we're going to buy. Negative sign, so we're going to sell. Positive, we'll buy. Negative, we'll sell. Here is, that's a positive, so we're going to buy. There's a negative, sell. There's a negative, sell. There's a positive, buy. X means it's a zero coupon bond. The S means they're shares. There's the X, so say a bond. There's the S, say the shares. X is bond, S is shares. You see where I'm going with this, right? This almost writes itself. So now all we have to do is figure out if it's ND1 or ND2. If it's shares, it's ND1. If it's a bond, it's ND2. There we go. Now, if we're long, if we're buying a call, that's easy. Everything is positive. ND1, ND2 if we're buying a call. If we're buying a put, we just put a negative sign inside the brackets. Because if you buy a call and you buy a put at the same strike price, one or the other is going to pay off. Period. You're going to win on one of them, you're going to lose on the other. But you have 100% of the area under the curve covered. So if this is N positive D1, this will be N negative D1, and same with D2. Look it up here now. Here we have ND1 and ND2. Again, look what we have in here, negative and negative. That's all we've done. That's all we've done here, okay? So that's nice and easy. If there's no negative sign in front of it, we're going to buy. If it's an S, it's shares. If it's S, it's ND1. If there's a negative sign in front of it, we're going to sell. If it's X, it's the zero coupon bond, and it's ND2. If it's a long call, they're positive. If it's a long put means we're buying a put, you still have no negative signs in front of the end, but you just stick negative signs in front of the bracket. Inside the brackets, you do the same thing. That builds itself. And all I did was say, well, just what are the payoffs? And then build your replication strategy. So if we were going to write it out in this kind of notation, all we have to do is just follow along. We have a positive sign in front of the S. We have a positive sign. We're buying ND1 minus, and here is X e to the negative RT and ND2. So there's how we price out a long call, buying a call. If we're buying a put, it's just the opposite. And again, with the negative signs in here, there's buying a put. We've seen this. This is where it might get a little bit tricky for you. Now we're going to sell a call. Now we're going to sell a call. So what happens here? Notice what happens here. A negative sign appears outside of the term S, negative N D1 minus this, negative N D2. That is selling a call. And if we're selling a put, all we do is we change the negative sign inside the brackets here. So the negative sign going from the call to the put, that's easy. But remember now, there's a negative sign outside for selling. Outside for selling. Why? Because we're selling. It's negative. So that's nice and easy to figure out the call and the put, figuring out where we're going on the call and the put in both sense. Now, because this is the same inside, look at what we're doing in here. This is the same inside. ND1, here is ND1. Forget about the negative sign right now. Here is ND1. Here is ND1. Right? We're going to get the same price. You're going to get the same price. Whether we buy the call or sell the call, you're going to get the same price. Why? Because if there's a call option, if you want to buy it, someone's got to sell it to you. They can't sell it at a different price than you're buying it. Every contract has two sides, a long and a short side. For every time you buy, there must be somebody selling. So you're both paying. You'll pay a price. The other person will receive that same price. They'll come up with the same price for the two. It's just a difference between here, it's obvious we're long the stock and short the bond. Here, we're short the stock and long the bond because we're negative and negative. Here, we're positive and negative, so we're going to be negative on this term, which is the stock term. So we're going to short whatever this term is. We're going to short that many shares and buy the bond. Here, we're going to buy the shares and short the bond. So the negative sign in front of here just tells us what we're doing. And again, can you figure this one out? If we're negative and a positive, that means we must be selling something of the bond. And a negative means we must be buying something of the stock. And are we doing that? Selling, buying. There we go. So if you can remember this, you should be able to build these statements. If you can build these statements, all you have to do is just follow along and you can build these statements as well. This should never cause you any confusion. All right, LOSI. Here, we're just going to introduce modifications to the BSM model for an underlying that actually has some carry benefit. So think about a stock. Up to now, we've used non-dividend paying stocks, European style options and non-dividend paying stocks. But let's introduce the dividend now to the stock and see how the call price incorporates that. We've always thought of calls as being not protected by the dividend, but in arriving at the call price, the dividend is considered. And same with currencies. If we have options on currencies, the currency has a yield. We can conceive of a currency as having a known yield. How do we deal with that? And that's all I'm really going to do is just introduce it because that's all we really need to do. So here's the formulation for the call and the put that we should be very familiar with. Here's the new term here, and here's the new term here, and look what happens over here. As we're going to introduce something called gamma here. This is the carry benefits expressed as a continuous yield. So it's e to the negative gamma t applied to s. And again here, And gamma, again, is whatever carry benefit we have. This does not necessarily have to be the dividend yield. It could be the rate on the currency as well, but this is how we introduce it. And then we're reducing this by gamma. Now, look what happens here, and this is pretty straightforward. I think you can get it. This lowers D1. If we have, because this was R plus, now it's R minus and then plus, so we're going to get a lower value for D1. We have a lower value for D1, we have a lower value for D2. Remember, we said we can think of D2 as the probability that ST minus X is greater than 0, or the probability that the call finishes in the money. That's what this is saying, that the final stock price minus the strike price is greater than 0 means the call's in the money. So if a stock pays a dividend, does it lower the probability that the call will finish in the money? Well, think about it. Let's say we have a stock at 100 and a strike price at 100 for 1 year. Well, every time the stock pays a dividend, what do we know happens to the price of the stock on the ex-dividend date? It drops by the amount of the dividend. So if that $100 stock is going to pay a $3 stock, we have to clear that $3 hurdle rate just to end at the 100. So the stock has to go up by $3 just to offset the $3 that it will drop on ex-dividend dates. So it does, in fact, lower the value of the call. But think about it in terms of a put. Well, every time that dividend comes off, the stock price drops. It actually increases the probability that the put will finish in the money. So the probability of the call being in the money drops as gamma rises. So the bigger the dividend, the greater the probability that the call will finish out of the money, the lower the probability that the call will finish in the money. Note, carry benefits lower the value of the underlying. It reduces the value of calls. It increases the value of puts. So if the underlying has a carry benefit, we will pay more for puts and we will pay less for calls. And using put-call parity, remember it was just S plus P. Well, there it is again. It's sneaking in there again. So we just have to remember to add that term in. So again, BSM applied to equities. We have, if we're going to use equities, we're going to use something called, this is delta. This is just lowercase delta, by the way. The gamma, we said, was our carry benefits. Generically, we just said gamma is a carry benefit. If we see lowercase delta, we're particularly talking about stocks. So applied to equities, the delta, the lowercase delta, represents a dividend yield, not just the dividend in dollar terms, but expressed as a yield. So you can kind of see that, well, you know, the dividend yield is not constant throughout the year, so it's kind of a close approximation, right? So it's just where gamma was, we just added in the lowercase delta. If it's to currencies, our gamma in that case is just the interest rate on the foreign currency, and you just substitute that in right in front of the stock price on both. You're reducing the value of the stock price. This is not a stock price anymore. It's a spot. Quote or a spot exchange, a spot foreign exchange. On this sense, there's the strike price. And of course, this is the option on the currency. Typically, if you're working with options and currencies, you're more likely to use an options on a futures contract, which is a nice segue into what we're doing next, which is we're looking at the black model to value European options on futures. So if you're dealing with currencies, most likely you're dealing with options on futures as opposed to options on the currency, on the spot itself. So that's all you have to do for equities with dividends, and for currencies is you're just adding one extra term in, which works to lower the value of the call and raise the value of the put. Okay, we're moving on to the black model. And what's different with the black model than the BSM is in the black model, the underlying for the option is costless to carry. So it's not a stock or an asset. At this point, it's a contract. We can think of it as a futures contract or a forward contract. So the black model is really for pricing out options on futures. And that can get confusing for some students who think, well, isn't that a derivative on a derivative? And it is. So how does this call option work on a futures? And I say, pretend the futures is just a stock that's free. Just pretend that that's the case. So let me give you an example. Let's say that we observe oil, CL. And let's look at the November delivery contract, which will be November 17th. And let's say that it is trading at $50. Well, we get the idea of a futures contract, right? That means at $50, it's trading at $50 right now, that if we enter into this contract, if we buy this futures contract, we are agreeing to buy oil for $50 a barrel under this contract, and this is for 1,000 barrels of oil. So if the price goes up, we benefit because we've locked in a price of 50. If the price goes up, well, we buy it for 50 and sell it at the higher price later on, or simply close out our contract at the higher price. Buy low, sell high, right? Well, this is for a futures contract. You don't get to pick your you don't get to pick the delivery price. The delivery price is the quoted price of the contract. If you don't like that price, you simply don't trade it. But a call option, we get to pick and choose. We can say, okay, well, I observe oil right now, as of this day, for November 17th expiration, this is the expiration of this contract, trading at 50. If I enter into this price at 50, if it goes up, I win. If it goes down, I lose. I might say, you know what? I don't want to risk all of that. But what I can do is I can buy a call on the futures contract, and I don't have to buy it at a strike price of 50. I can say, I'm going to buy the $55 calls. Because the $55 calls will be cheap, or at least cheaper. So what's my downside? Well, whatever I paid for the call. That's all I risk, is whatever I paid for the call. My upside is, well, if this gets above 55 plus what I paid, I make money. So rather than buying the contract, I can buy a $55 call. What I cannot do at the futures level is enter into the November 17th futures price at $55 because it's trading at 50. That contract is trading at 50. So I cannot enter in at 55, but I can set the call to be 55, and the call, of course, will set my exercise price, and the $50 happens to be where the futures contract is trading at this point in time. So if you think of it like a stock, it's the same thing. We see a stock at $20, we might buy the 3-month 2250 calls. Well, think that's the same thing. So if we get confused over the fact that it's a futures contract versus a stock, just pretend that the futures contract is a stock. Just pretend that it is, and guess what? In your mind, it works out perfectly. All you have to remember is, well, in this case, the futures contract didn't cost me anything to buy. It's costless to enter. So let's have a look at what we have there. You'll notice that we pretty much have the same, thing. Let's take our ND functions out of here for now. What do we have? We have F naught and, of course, T. That is saying that whatever price we see today, so for example, we were looking at this contract trading right now at 50. That's the price we lock in for time T for November 17th. So that's the price that will go there, multiplied by some probability minus X. What is this X? X is not the contract price of the futures now. X is the strike price of the option that we bought. We can buy deep in the money, at the money, or out of the money. So X, and then of course scaled by its probability. Well, ND2 is the probability that the call will finish in the money, which means it'll finish over $55. That's the probability associated with that. This is the conditional probability of what the price will be if it is over the strike price. Remember, this first one's the conditional probability. So this is really just the payoff in here. And this, well, this is the expected payoff because we're multiplying it by probabilities. It's not the payoff. F naught minus the strike price, there's your payoff. Well, this should be, to make it a true payoff, we actually can take this out right now and call it at that future time FT, whatever it is at that time, will be whatever we entered it in at, whatever the contract price we observed that day was, whatever the futures price is at that time in the future. I get confused sometimes. Minus whatever strike price we locked in. There's the payoff. Once we scale it by probabilities, we're talking about an expected payoff at that point in time. And of course, this is a present value factor. It says, hey, get that all the way back today because we're buying it. So what is the call? The call is the present value of the expected payoff. How do we get the expected payoff? It is the price, assuming it's higher than the strike price, minus the strike price. Now, of course, weighted by their probabilities. The put is just the other way around. So we could just conceive of it that way. So How do we describe it? Because really, what is our learning objective here? And I really want you to stay close to this, because if you go too far into, I really, really want to understand all the depth of the model, it's not necessary. And there's already too much to do, and it's not necessary. If you want more, take the FRM, do the FRM, you will get more there. And then you can use all of that cognitive energy to pass that test, diving into that. But it's not necessary here, so any question on derivatives you'll get will pretty much give you a lot of the output and the input, and the calculation you won't have to do. You'll just have to recognize what the inputs are, and with the output, what it means, how we can describe it. So we can describe a call. Here we have a call, for example, 51.41, and the put is 59.76. And here's our ND1, N negative D1, ND2, and N negative D2. Notice that this must add to 1, and this must add to 1, because if you just put the negative in there, ND1 and N negative D1 is all the area under the curve, so it must add to 1. So let's see if we can talk about what a call is here, or describe what the call is, being that we have these probabilities now. So the call is just the present value of the expected payoff, and the expected payoff is 0.491 times the futures price minus 0.50, not 509. I'm going the wrong way. I'm going across. I got to read down ND1, ND2, minus 0.461 times whatever exercise price we have. So that's the value of the call. It's really just the present value of the expected payoff, and these are the expectations. And the put, we can sort of describe the same way, as the present value of 0.539. Here we're going from the bottom up, right? Negative D2 to negative D1. 0.539 times the strike price minus 0.509 times the futures price. There we go. This is really all you have to do. There are two big takeaways here. Takeaway number one is the black model is used for pricing out calls on futures and forwards. We need a different model because those assets are financial contracts are costless to carry. And you need to be able to interpret what the output is in terms of the probability, in terms of the call and the put being expressed as a present value of the expected payoff. Okay, I thought it might be useful to look at, in picture form or in graphical form, what ND2 is trying to capture here. So let's say that we're at this point in time over here, and we can observe a futures price, or it doesn't even have to be a futures, it could be the price on anything. On anything that we're buying a call option on. I have got the futures price here. And we expect that there'll be some expected value for it over some period of time. But it doesn't have to take this value. It can basically follow any path along here. You can even do this, right? It can follow anything. But we expect a distribution of prices that look like that. Well, at this point in time, if we're buying a call option with a strike price way up here, we simply just say, well, okay, this area under the curve up here, that's the probability of N2. ND2 will measure this area under the curve here, which is why some like to say, you know what, that's the probability of the call finishing in the money. And I really don't like that interpretation. I think I've been clear on why I don't like that interpretation. If the strike price, if we bought a strike price that was already in the money on day one and extended it out, we've got a much higher probability that the option will finish in the money. So think if you could go as deep in the money as you possibly can. As deep in the money, ND2 would approach 1, would approach 100%. So if there was such a thing as a call option with a strike price of 0, you're actually buying the underlying, isn't it? Think of a stock at $20 and you bought a call option on that stock with a strike price of 0. In essence, you've bought the stock. So what's the probability that the stock will finish above the strike price of 0 with a stock is 100%. ND2 would be 100%. ND1 would also be 100% as well. So the deeper in the money you go, let's read what we have here. The further out of the money the strike is, the lower the probability of exercise. So even if we have a futures contract at, let's say, $45 and we bought a $50 call, if the futures price finishes at $49, that call is worthless. It's out of the money because it has a strike of 50, right? The lower the ND2 on this, the further out of the money the strike. Out of the money means the higher the value of the strike of the call, right? The further in the money the call, the higher the probability of exercise. So there's where we capture ND2. Now, for some of you sitting out there going, I think he's drawing it wrong, you're half right. You're half right. Basically, this is, if we look at the distribution, ND2 captures this. ND2 is meant to capture this. Well, what am I doing way on the other side here? Shouldn't I be up here? Am I not doing this wrong? I believe I'm doing this wrong, right? Somebody would look at you and say, you're doing it wrong. Well, no, I'm not. I want you to do something for me right now. I want you to anchor this. Drive a nail into the corner of this distribution over here and leave this side free. Then I want you to pull this towards you. Then I want you to start lifting it up as if you're pulling it around in a circle to the top. And that's what you would get. So imagine that you're laying on your side. Let's see if I can get you laying on your side here. I went to art school, so it's about time I put this art to good use. And there we go. And you're looking at this distribution from behind. So you're looking at it from behind. It's the same thing as laying on your side this way. And I can't draw your eyes. And then looking at it from the front like this. So here is how you should be looking at it. So imagine that you're laying in behind the distribution now, looking inwards. So you're way off in the distance over here, let's say, and you're looking at it this way. That's exactly what you would see. So I have drawn it right. Now ND1, what is ND1? We're saying ND1 is the value of whatever it is that the underlying, here we'll say it's F naught. It's the value of F naught given that it is above the strike price. So all of a sudden the probability space is only this much, not the full curve. So ND1, by definition of a conditional probability, will always be greater than ND2. I don't know if that helps. Maybe it does. Maybe my little drawing here wasn't as good as it could be. But if you can conceive of ND2 as looking like that depending on if we raise and lower the strike, we raise and lower the value of ND2. All right, let's move on to the next learning objective and look at the black model as it applies to interest rates. We're going to look at interest rate call and put options. And the first question we have to answer is, well, what is the underlying of an interest rate call option or put option? And the underlying is a forward rate agreement rate. Not a forward rate agreement, a forward rate agreement rate. In other words, it's the rate we would find in an FRA for that same period of time. And that can be a little confusing in words, so let me explain what I mean. Let's assume we have a timeline that looks like this, and let's make this 1 year. From the first X to T1 is 1 year, and that's a call option on, and we'll make T1 to T2 3 months. That's a call option on a 3-month rate. So the call option expires at T1, and it is for this 3-month rate, whatever that 3-month rate happens to be. And we will know what that 3-month rate is at T1. It'll be whatever the floating rate for 3-month LIBOR happens to be at that time. Well, this rate over here is a forward rate. If we have a spot rate from today to T1 and we have a spot rate from today to T2, we know today what that forward rate is that is implied by the spot rates. Well, because we know that, if we look at an FRA for that period of time, whatever the rate is in the FRA, that is the rate. So in other words, the underlying of an interest rate call option is the FRA rate, which is a LIBOR rate. Not an FRA, the FRA rate. There are some problems with using this for pricing out the call option, and it's the day count convention. It can get a little bit messy. For an FRA, the day count convention is typically 30, 360, or actual 360, especially when we're looking at different currencies. Bank deposits in different countries typically use actual 360. Corporate rates 30, 360. So the day count convention can be either actual or 30 over 360. However, the day count convention for options is actual over actual. And when we get down to the calls and the puts, I'll show you where the difference in that lies. So Let's begin. Here's the call, here's the put, and here's the formula that we've been used to so far. All we're going to do is we're going to substitute something different in here. This is the FRA rate. It's not the FRA. I want to be clear. We're not saying that the underlying of an interest rate option is an FRA agreement. It is the rate that we typically would find in an FRA agreement for the period of time that the option applies to. So FRA scaled by ND1 minus the exercise rate scaled by ND2. Notice that this is a rate and this is a rate, so it's the difference between the two rates. And then, of course, discounted back. This is the accrual period of the option. Notice it goes to T2. It goes to T2 because the option, a one-year option, expires here, but since it's for a 3-month rate, the payoff of the option would be over here. So we have to discount the payoff all the way back, or in option terminology, the expected payoff would be discounted all the way back. So it's to T2, and of course this is going to be actual over actual day count convention. This AP over here is the accrual period. That is this period right here. It is the accrual period of the FRA rate, and this will either be 30 over 360, or if it's any different period of time, if it's 46 days, it would be 46 over 360. It would be either 30 over 360 or actual over 360. So that's all we have to worry about. It's the FRA rate minus the exercise rate, discounted back for the accrual period of the option, and of course scaled by whatever the accrual period is for the rate that we're looking for. And the put is just the opposite. It's the exercise rate minus the FRA rate, again discounted back for the accrual period of the option, scaled for the accrual period of the FRA rate. When you're calculating D1 and D2, gets a little bit messy over here. The T that we're using in D1 and D2 is T1, not T2. It is the end of the call period. So if it is a 1-year call, this is 1 year. If it's a 1-year call on a 3-month rate, then the payoff happens in 1 year and 3 months. So the discount period will be 15 months, but this will only be 12 months because the call option expires and is dead in 12 months. And in 12 months it's dead because we know what the rate will be at that point in time. Let's look at some interesting things we can do with the interest rate options when we start combining the call with the put. You'll recall on the last screen I said that the underlying of an interest rate option is a forward rate agreement rate, not a forward rate agreement now, just the rate in the FRA. There is nothing saying that the strike price of any option has to equal the FRA rate, but if it does, we'll draw out some examples here where we make it equal. If the exercise rate on an option equals the FRA rate, we can draw a nice little graph here with a straight line, XR equals RK. If we buy a call with a strike equal to RK, and we sell a put with a strike equal to RK, we've basically created a synthetic swap, a receive floating, pay fixed swap. So let me see if I can prove that to you. Let's say that the exercise rate was 6%, just for argument's sake, and we'll work it out here. So we have a pay fixed swap, which means we would be paying 6%. And we would be receiving whatever the floating rate happens to be. So let's see if this actually works out with our call option and our put option. So if this is 6%, anything above that 6% we get. So this shaded in area up here, this is what we would receive from the call option. The put option wouldn't be worth anything at that point. We would get everything above the line. So in other words, we would receive the floating rate, but would still be paying the fixed rate because we'd only get the difference. We'd only get this. So if this were 8%, what would we get? We would get 2%. That's the same as receiving 8% and paying 6%. Receiving floating, paying fixed. If, on the other hand, the floating rate at this point, or the interest rate that we observe at this point in time were 4%, what does that mean? Well, everything under the line is what we would pay. So if this were 6%, and this is 4%, we have to pay the 2% difference. That's the same thing as receiving 4% and paying 6%. Receive floating, pay fixed. The net result is we're out 2%. The net result up here was we're up 2%. So by being long the call and short the put at the same strike as the FRA rate, we have created a synthetic swap, a receive floating, pay fixed swap. It doesn't take much to see that if you reverse it, instead of a long call and a short put, we go with a short call and a long put, everything just reverses. We create the opposite type of swap, a received fixed, pay floating swap. We can also use interest rate options sequentially over time, let's say 6 months, 1 year, 1.5 years, to create what's called a cap. And a cap would be a cap on, let's say that we wanted a floating rate loan, but we didn't want to pay over a certain amount of interest. We could buy interest rate call options on each payment date that we had to make. So if we were making payment dates every 6 months, we could buy call options on every single one of these. Obviously, if we go to a dealer and say we want all of these call options, the dealer would say, look, it's easier to bundle all in one contract. We'll call it a cap, and all of the calls we'll just call caplets. And this is how this works. Let's say that the strike price is XR. In other words, you bought a call, so you own everything over XR. If at 6 months the interest rate is at this level, that's what you pay. You pay all of this in interest. At the 1 year mark, if the interest rate is at this level, well, the call pays off, so you would receive anything above the strike price. So you receive all of this. You still pay this higher rate in the market, but because you receive this, this is all you pay. You're capped at that rate. 1.5 years go by, the rate is at this level, you pay this rate. Notice the option finishes out of the money here, you get no payment from that. So no matter what happens, every time the interest rate that you pay on a coupon date exceeds the option price on that date, you would receive a payoff. You pay the higher rate in the market, you receive the payoff, which means net, you pay whatever the rate was in the cap. Well, before we actually get to floors, I ended the last one by saying, guess what? Thinking that the next screen was going to be floors, but it's not, and I don't feel like redoing the last screen to edit out that point, so I'm going to say, hey, before we get there, let's look at a cap in an actual numerical example to see exactly how this thing works. So let's say that we're just going to use a binomial model to do it, well, a two-period model. This could be days, weeks, whatever the case is. Let's say we have a notional amount of 100, and the strike price on our option is 5.75%. This is our XR, and it's a semi. And let's say that the rate right now is 5.54. It can take two directions, and then if it went up, it could take another two directions. Let's follow the up on this one. So this is time period 0, this is time period 1, time period 2, and this is the rate at the end of that time period. This is the rate that we would have to pay. So at time t equals 0, 5.54, r equals 5.54, our option is out of the money. So if this were our first expiration date, our option is out of the money. So the company receives from the option, the company receives 0. And the company pays what? Well, this is semi-annual. It pays 5.54% on an annual basis, semi-annually. So it'll pay $277. Nice and simple. At T1, R is 6.004%. XR is now in the money. So our call option is now in the money. So what will we receive? Well, we take 6.004 minus 5.75. And that's on an annual basis. If we divide that by 2, we will find that we receive 0.127. So we'll receive 0.127, but we will pay the 6.004 rate. And semi-annually, that'll come to 3.002. And if we net the 2 out, what do we pay? 2.875. Well, 2.875 is the call price, 5.75 divided by 2, because it's semi-annual, right? So there we go. We're capped at 2.875. When the market rate is lower, we pay the lower rate. When the market rate is higher, the call will pay off. We'll pay the market rate, but it leaves us capped. Let's go to 6.915. What happens over here? Well, at t equals 2, r equals 6.915. Our call option is still in the money. In fact, it's even more in the money right now. So the company receives what? 6.915 minus 5.75 gives us the spread between the two. Since it's semi-annual, we divide it by 2. We will get 0.5825. 6.925. But we have to pay, we'll pay 6.915, of course, divided by 2. So we'll be paying out 3.4575. And what is our net on this? If you net it out, what do we get? 2.875. 2.875. Capped at 2.875. Just to show you where I'm getting that. There's the 5.75, right? But since we pay that semi-annually, we divide it by 2, we will get 2.875% on each payment coupon. So there we go. So you can see that we've capped it. So basically, here's our 5.75. Here, there's no payoff, so we get a 0 payoff when we make if this is the rate at the beginning of the period, we usually pay our payment at the end. We would pay 0. Here, we have a payoff over here that would be 0.127. And over here at t equals 2, at the end of that period, we'd have a payoff of 0.5825, 0.5825. There we go. So that's basically how a cap works. We sell a bunch of calls on every single every single coupon date that we have. And if the market rate is higher, we'll pay the market rate, but the call will pay off, thereby capping us. Okay, let's have a look at a floor. Let's say that we have a floating rate investment with a floor. We put a floor in place. So we're getting a floating rate on our investment, but there's some level below which we're just not comfortable on, so we can buy puts. So we buy puts at the 0.5 year, at the 6 month, at the 1 year, and the 1.5 year rate. And let's say we observe a market rate down here. The put is in the money, so the put pays off, thereby bringing us back up to the floor rate we wanted. At the 1 year point, the rate is way up here. Well, guess what? We get that. The put ends out of the money, so the put doesn't pay off anything, so we get that rate. 1.5 years, the rate is here, so we're below the market rate. The put pays off because the put is now in the money. So the put pays off, bringing us back up to that floor. Each of these legs is called a floorlet. The sum of all the legs is called a floor. So if we have a floor and we have a cap, the cap costs us money to enter. The floor costs us money to enter. If we're long a floor, we received a fixed rate. If we're short a cap, we pay a floating rate, right? So if we combine the two, receive fixed, pay floating. Long a floor, short a cap. So we're long one, short another. You could do it opposite as well. You could have gone long a cap and short a floor. This is just an example. They cost money to enter. So if we short a cap, we're going to get money. If we're long a floor, we're going to spend money. If, remember the assumption we made now at the beginning, if the exercise price was also the rate in the contract, the cost of entering the short, the cap, and the cost of entering the floor at the same rate will be equal. Hence, it will be free to enter this. The money you get from selling will pay for the money it costs to enter the call. So the two will enter. The two costs will offset each other. You'll receive fixed and pay floating. Well, what is that? That's a swap. That's a fixed for floating swap. Why? Because you have a series of payments. A series of payments now, but you've entered into a combination of options, a portfolio of options that create a floor, a portfolio of options that create a cap, in such a way that you now have a fixed for floating swap. If the exercise rate on the call and the puts equals the swap rate, the value of the cap will equal the value of the floor, therefore it costs you 0 to enter. So if you can set up a bunch of options that mirror the same thing as entering a swap, you should be indifferent between the two. You can say, look, here's a swap, but I can also recreate the swap with a series of options, a series of puts and calls. Well, that last conversation sort of led us right into the idea of a swaption. And a swaption is an option on a swap. Rather than getting involved in all those caps and floors and put it together to get a swap, why not just create an option on a swap? Here, the holder has the right to enter into a swap at a pre-agreed swap rate. That's the exercise price. So we don't really call them calls and puts. We call them payer swaptions and receiver swaptions. The first word refers to the fixed leg, pay fixed or receive fixed. So the payer swaption will pay fixed, get floating. The receiver swaption will get fixed, pay floating, as opposed to saying calls and puts. We just use these two terms. So how does this work out? Well, let's say that the swap rate increases before expiration. We're holding an option on a swap. So we have a swaption, and let's say that the rate increases. What the buyer can do, the buyer of the option, can then enter into that swap at whatever the rate was at the exercise price and pay the fixed rate at the exercise price and get floating, because that's what the swap is. So let's say that the contract rate was 3% and fixed rates are now 5%. The holder can enter into this contract to pay 3%. If the current market rates are 5, they'll pay 3 because that's the rate they locked it in. They'll get 5. Now, what they can do immediately after they exercise the option, they are into a swap where they're going to pay this fixed rate and get floating. They can enter into an offsetting received fixed pay floating swap. Okay, so add the two together. If on this one they're paying fixed and getting floating, and over here they're paying floating, they'll pay. Notice that the floating legs will cancel each other off. So what do we have? They're going to pay fixed at this exercise rate, which was lower than the market rate, but they're going to receive fixed at a higher rate. The floating legs cancel off. So what do they have? They just have the difference between a known fixed rate, which is XR, the exercise price, and the current fixed rate. The floating legs offset, and they end up with an annuity, which is the fixed rate, whatever the fixed rate is at that time in the future, minus whatever the exercise rate is on the option that they entered into, that they then exercised. So the present value of that annuity is really just the difference between the two rates times the notional amount for however many payments that has to occur. And we'll get a present value of that annuity. We're going to use that in the black model in just a second. So how does the black model change when the underlying when we're talking about a swaption as opposed to a call or a put? When the underlying is a swap, the pay swaption, here's the pay side, the receive side. Remember, we called it a pay swaption and a receive swaption. The pay swaption is the fixed rate multiplied or scaled by ND1 minus the exercise rate scaled by ND2. Remember, this is the probability of the rate being in the money. This is the value of the rate or the expected value of the rate given that it is already above the strike. And there's the present value of the annuity factor. And this is just a present value factor because this will end up being an annuity. This is just saying that you need to find the present value of that annuity. And we have the same thing here for the receiver swaption with D1 and D2 looking like this. It's important to note here that the T within here is when the swaption expires, not when the when the swaption expires, not when the swap expires, but when the swaption expires. E to the RT here. Where is the discount factor in all of this? Why are we not discounting it backwards? Well, since the payment is a series of payments, it's not just one payment, it is a series of payments. The present value of the annuity embeds the discount factor in there. So that's why we don't see this discounted back to the day by e to the negative RT, is because this is not one payment. What we have in here, this payoff here, is a series of payments. This actually brings back, this is instead of e to the RT, we'd have to have e to the RT for every single payment that's embodied in this swap. So the present value factor is doing the heavy lifting for that one there. All right, let's go through the 5 Greeks. You recall earlier in the video series I changed the H to a delta when we were looking at the binomial model. For the hedge ratio, I changed it to a delta, saying that's eventually what it's going to mean, so let's just call it that now. Well, here we are at delta. And what does delta measure? It is the change in value of the option for a change in the price of the underlying. And the underlying itself has a delta of 1. So if the underlying is a stock and the stock changes by $1, how much does the stock change by? It changes by $1. It changes 1 to 1 with itself. But depending on the strike price we have on the option, a stock, just because the underlying goes up $1 does not mean the value of the option will go up $1 if it's extremely out of the money. And let's say it's a really long dated option, like a 2-year option that's really out of the money. If the underlying goes up maybe even 10%, that call option might not even move at all. The value of that option might not even budge. It might have a delta that's so low that it might not respond at all. So delta tells us how the call will increase in value or change in value based on how the underlying changes, or based on the magnitude of the change in the underlying. So delta sort of looks like this. Delta for the call, delta for the put, and this doesn't look very appealing at all. E to the, this is a lowercase delta up here as opposed to uppercase delta, lowercase delta. Negative delta T on both of them. The call, of course, ND1. They put N negative D1. So this is an important thing right here that I want to draw your attention to before we go much further. When we add up whatever these two are, whenever we add them up, you will get to the full value under the curve. It will add to 1. It must add to 1 because it's the entire area under the curve. And this becomes important later on when we want to do synthetics. A synthetic is, how can we put options together that exactly mirror the payoff of the underlying? In that case, we are equivalent to holding the underlying, but synthetically, not real, right? So for a given X, delta on the call plus delta on the put will equal 1. And we see that right here. We see it right here in the ND1 and negative D1. If you add the deltas together at the same strike price, at the same strike, you can't take a call with a strike price of $20 and a put with a strike price of $22.50. That doesn't work. But at $25, let's say a stock at 25, and you're looking at the call and the put, the deltas on both of them will add up to 1. Or, I should say, in the real world, very, very close to 1. Very close to 1. Sometimes you'll get 1.01, 1.02. But typically, we would just say they will add up to 1. All right, let's take a little closer look at delta. There's a little bit of a problem with delta, and this graph sort of shows you what the problem is. For large changes, delta loses accuracy. For small changes, let's say whatever the stock price is, if the stock price moves a little up or a little down, delta will be very good at telling us what the call price will be for small changes on the way up and on the way down. However, for large changes up or large changes down, delta doesn't work because delta will give us some linear approximation to what the call will be. But the true call value follows more of a it is non-linear. It will follow a non-linear path. So for small changes, delta will get us very close to what will actually happen in the price of the call, but as you start getting larger and larger changes, it doesn't work out so well. So for small changes in S, the option delta is fairly accurate. For larger changes, delta loses accuracy. I think on this screen you can really see how octagonal all the letters are here. You can see how they don't want to make a nice smooth round circle. Like look at ACC. That, I mean, it just looks like I'm suffering from the DTs here, but I'm not. I'm quite drunk right now, so I can't possibly be suffering from the DTs. But look at this. This is just, every time I look at this, it's just upsetting me. It's just upsetting me. Anyways, I just got to move past this. I'm going to need therapy, lots of therapy for this, I think. So what is delta hedging? Delta hedging means taking an offsetting delta position so as to be delta neutral. So let's say that I'm long 100 shares. Basically, I'm long 100 deltas. The underlying has a delta of 1. So if I'm long 100 shares, I'm long 100 deltas. I can sell 2 at the money calls. At the money calls typically have a delta of 0.5. If you're at the money, you typically have a delta of 0.5. So if I sell 2 at the money calls, that means I will be short 50 times 2. 50, there's 2 calls, there's 50 deltas, right? Because each call is for 100 shares. If the delta on the option is 0.5, and the underlying of the option is 100 shares, that's 50 deltas. I will be short 50 deltas times 2 options. So I'll be long 100 deltas by being long the shares. If I sell 2 at the money calls, I am now short these deltas. So if the shares drop by a small amount the next day, my position will lose money, but my call option should increase by a like amount, thereby hedging me out on that. Here's the important thing about delta hedging. It protects from small moves up or down in S. Small moves. And when you delta hedge, you're really delta hedging for a day, maybe 2 days before you have to adjust that hedge. Because delta changes with moneyness. Let me say that again. Delta changes with moneyness. So let me see if I can give you an example on this chart right here. So let's say the stock price moves up a little bit to here. We can see that the delta sort of approximates the move. So if I delta hedged at this point, let me say X marks the spot. Let me say I delta hedged there and the stock moved up by a little bit. It would be okay. But if the stock keeps moving up by the same small amount each day, I'm way off. Once it moves up a little bit, the delta at each level as the underlying moves up in price, delta also starts to change. The more in the money it gets, the higher the delta goes. The more out of the money we go, the lower delta goes. So this delta hedge for this 100 shares is at a certain price of the underlying. As the underlying moves away from that price, this hedge will no longer continue to protect me, which means I will have to continually modify my delta hedge. So you never delta hedge once. So let's say that over the course of the day, today, I think, it's going to look like an ugly day. I think there's going to be some bad news or some volatility in the afternoon, and I want to hedge myself out just for one day. Just for one day on certain underlyings. I can delta hedge that day, and I should be okay for that day. But if these moves spill over into the next day and the next day and the next day, that's not going to help me very much. I'm going to have to continually adjust my hedge. All right, let's get a little bit more formal on our delta hedging here. Being delta neutral implies that my portfolio delta plus the delta of the hedging instruments collectively will equal 0. Once I get to 0, if I have 0 deltas, I'm delta hedged. Why are we adding? And you'll see in a second when we calculate NH why we add. And I don't mind that addition in here. I'm not going to argue that, well, all the positives and negatives here. I want the addition in here because I want to see the sign in front of NH. So what are we saying here? Let's take our portfolio delta. On the last screen, we said, let's assume we're long 100 shares. Our portfolio delta in that case would be 100. Well, to get to 0, I know I need a negative 100 here. So what do I have? I have the number of hedging instruments I need multiplied by the delta of the hedging instrument. So maybe I need to figure out, well, how many instruments do I need? I can observe the delta of the hedging instrument. I just got to figure out how many I need. And that's what NH does. It tells me how many I need. It is negative portfolio delta because the portfolio delta is what I got to get rid of. So let's put that negative sign in front of there to denote that you got to get rid of that. Divided by the delta of the hedging instrument. So we have 100 deltas we got to get rid of. Put the negative sign divided by each call option has 50 deltas. That gives me negative 2. The sign tells me my position. This tells me my size. I need 2 contracts. Negative 2 means I must be short 2 contracts. So I don't mind the negative sign being associated with this as opposed to putting portfolio delta minus this delta. It is plus a negative, which will get me to 0. So let's look at an example of this. A little bit of a tricky example, but let's look at one here. And we'll hedge 2 ways. We'll hedge our position. Here we have a position of just puts. We'll hedge it out with the underlying, and then we'll hedge it out with calls. So let's say that there's a stock price that is 100. Our puts, because we're short puts on 10,000 shares. Let's say we have an exercise price of 100, so we have at the money puts. R is 5%, risk-free rate 5%. The time to expiration of the options is 1 year. Underlying volatility is 30%, and the underlying has a dividend yield of 5%. We are short puts on 10,000 shares. Hedge it out. Well, the first thing we have to say is, well, okay, well, what's my current delta position? Am I long delta or am I short delta right now? Well, if we look at our short puts on 10,000 shares and we look at our delta on the call, with a strike of 100, it's 0.532. On the put, it's 0.419. I don't like this example. I got this example out of the book. Let me tell you why I don't like this example. This does not add to 1. It has to, because the strike is 100. So the call, the delta on the calls and the delta on the puts must add to 100. So whoever wrote the question lacks a fundamental understanding of just that basic rule. But let's just say it's an example, a wild, crazy example, just to see if we can hedge it. That's fine. Let's focus on that. Well, are we long or short delta? The delta on the put is negative 0.419. We have 10,000 puts on 10,000 shares. So if we multiply 10,000 by 0.419, we get 4,190. But negative 4,190 delta. So the motivation might be to say we are short 4,190 deltas. But we're not. That is the delta on that position, but we are short that position. So if we're short a negative, we're actually long, right? So we are long 4,190 deltas. Now, does that make sense? Well, if we're short a put, where do we benefit? Do we benefit when the price drops or when the price increases? If we're short a put, means we sold the put. We don't want that price to go down. We want it to go up, which means we are long. We're in the same, we are on the same side as somebody who's long the stock. So we're long 4190 deltas. How do we delta hedge with the underlying? Very simple. We short. We will short 4,190 shares. There, now I've gotten to delta 0. Well, what if we want to use calls to hedge that out? Well, what is our current portfolio position? Remember, it's negative, and our portfolio delta in this case is 4,190 divided by, what's the hedge on the call? 0.532. 0.532. So if you divide that, you get negative 876 calls. 876 calls. So what are we doing here? We're going to sell 7,876 calls. Well, let's think about what happens when we sell calls. Are we hedged at this point? What direction in price of the underlying would we like it to go? If we sell a call, we don't want it to go up. We want it to go down. So if our portfolio position benefits from an increase in price and hurts from a decrease, to be delta hedged, we need something that does the opposite of that. If we're short calls, that benefits from the decrease benefits from the decrease and hurts us on the increase. Here we hurt on the decrease. Here this benefits on the decrease. We are delta hedged. All right, let's move on to gamma. Gamma, you can consider it the second derivative. If the delta is the first derivative of the rate of change of the stock price, gamma is the second derivative. It is the change in an option's delta for a change in the underlying. Remember, delta was a change in the call price for a change in the underlying. Gamma is a change in the option's delta for a change in the price of the underlying. So as an example here, let's say the stock is $50. We have a strike price of 50. We observe a delta of 0.5, which we should. This is an at-the-money option. Delta should be 0.5. And let's say the gamma is 0.03. All I'm about to show you is how gamma comes into play. So we said that delta will tell us the change in the value of the call for small changes in the value of the underlying. So if the underlying goes from 50 to 51, being that we have a delta of 0.5, we'd expect the call to go up by 50 cents. However, as S0 goes from 51 to 52, because at 50 we have a delta of 0.5 but a gamma of 0.03, so going from 50 to 51 we should rise by 0.5, but the delta at 51 will now be 0.53. So as the underlying goes from 51 to 52, the call option will go up another 53 cents, not 50 cents. So gamma will tell us how delta changes as the underlying changes. Again, we go from 50 to 51. We should get the delta we observe when the stock is at 50. But now at 51, because gamma was 0.03 at this rate, at 51 we would expect delta to be 0.53 at 51. So as it goes to 52, it will go up by 53 cents. It is the measure of the curvature in option price versus the stock price. Remember we had that on the last screen where we looked at the true call price, and delta only got us like this. Gamma kind of measures the curvature, not precisely, but does a very good job. Gamma on the call equals the gamma on the put. No matter where you are, gamma is the same. So if you look at a set of options at the same strike price, you'll get two deltas. You'll get delta for the call, delta for the put, but you'll only have one gamma. Some option, when you're first introduced to option trading, you may be looking, going, but what option does that gamma apply to? That's for both. It's for both. And gamma looks like this. It's just this formula here, scaled by ND1. Now, notice it's a lowercase n. That's the probability function, not the cumulative function. It's just the probability function. So, at S and X, when we say S and X, let's take a stock price and a strike price that are the same. Delta C plus delta P we know adds up to 1. The stock price and the strike price are the same, so if we have an at-the-money option, we know that delta C plus delta P will add up to 1. Let little g be the change in delta. Let big G be the change in S. I'm about to say something important here about gamma here, and I'm about to prove why there's only one gamma, why there is only one gamma. Do you get this statement here? The delta on the call plus the delta on the put equals 1 for S and X. Great. Let's add G to S. Let's increase the stock price by G, and we still, of course, have the same X, which was just S. So the stock price is G higher. The delta on the call would increase by C plus G. Gamma is the rate of increase in delta for a change in the price. So the delta would increase by C plus G, but the delta on the put would be P minus G because it must add up to 1. Remember, they're still at the same strike. It does not matter where the stock price is. As long as the call and the puts are at the same price, their deltas must add to 1. So if gamma is the rate at which delta changes for a change in price, that means when the delta of the call increases by G, the delta of the put must decrease by the same G to be able to equal 1. Hence, there is only one gamma. Let me be clear on what I just said there. Let's say that, because we have a stock and a strike price at the same level. Let's say that we observe our stock price is at $100 and our call price is at 20. That's a deep in the money call. That's a deep in the money call. It doesn't matter. If we take the call with a strike price at 20 and the put at a strike price of 20, you'd still get this. Even if you change this to 30 and you took the call and the put at 30, even though the underlying's at 100, you'd still get this. Let's say you did it at $330 when the underlying's 100. This relationship still holds. So if gamma increases delta on the call, for this relationship to be the same, it must decrease delta on the put by the same amount. Hence, when we say that gamma on the call equals gamma on the put, I don't know how much more proof you can get than that. The gamma of the underlying is 0. The gamma of the underlying is 0 since delta is constant at 1. Delta never changes. No matter where the underlying price goes, its delta will always be 1. Since its delta never changes, the rate of change of delta of the underlying has to be 0. It never changes. It has a gamma of 0. The underlying will always move 1 for 1 with itself. All right, gamma is always non-negative. And is the largest at the money. Remember now, the stock itself has a gamma of 0. You can't have a negative gamma. You can only get down to 0, and gamma is never is always non-negative. Gamma is very small when it's deep in the money or deep out of the money. It measures the risk that remains once a portfolio is delta neutral, and you'll recall when I said that when we got delta neutral, it was only for that particular price at that particular time, and that hedge might last a day, maybe 2 days before you have to re-hedge. Because as the underlying moves, the moneyness of the options move, which means the deltas move. Gamma risk can be managed to a specific level, but never eliminated. You cannot get rid of gamma risk. Once if you're trying to delta hedge, you can't get rid of gamma risk. You'll always have gamma risk, but at least you can manage the level of your gamma risk. You just can't get rid of it. Let me show you what I mean here. Let's say we're long 100 shares. We have 100 deltas. Let's say we sell 2 at-the-money calls, and you'll recall that I said an at-the-money call will have a delta of 0.5. And if we're long 100 shares, each option's for 100 shares. That's 50 deltas, and if we're short 2, we're selling 2, we'll be short 100 deltas. But the at-the-money calls have the highest gamma. We set it up here. Gamma is always non-negative and is largest at the money. So we're delta neutral, but we have very high gamma. Can we do it a different way? Can we manage it? Can we get delta neutral and manage our gamma downwards? Remember now, we just want to get neutral. We can sell deep in the money calls. Gamma is very small when deep in the money. It has the lowest gamma. A deep in the money call will also have a very high delta, however. So the delta on this is 0.8. Now I would say if you're long 100 deltas and you got to get short 100 deltas, you would sell 1 1/4 options to get the 100. You can't sell quarter options. You really can't. So what we're going to do is we're going to modify our position both on the underlying and on the options in 2 different ways to hedge. The first thing we can do is sell 2 calls and buy 60 shares. And that puts us delta neutral with a very low gamma. So we've managed gamma very, very low and we're delta neutral. We buy 2 calls, sell 2 calls, we'll be short 160 deltas. We're long 100 deltas, so buy another 60 shares would make us long 160 deltas. If we don't want to add to our position, what we can do is we can sell 1 call and sell 20 shares. If we sell 1 call, we'll be short 80 deltas. We're long 100 deltas. If we sell 20 shares, we'll be delta neutral with a very low gamma. Typically, you don't like managing the underlying this way to delta hedge. You typically don't. But typically, if you're delta hedging, you're not doing it with 100 shares. At 100 shares, it's like, whatever. It's 100 shares. Let it ride, right? I mean, let it ride or sell it. You can't hurt yourself selling 100 shares. But if you got 3.5 million shares of something, well, guess what? You're going to hurt yourself trying to sell that position. You're not going to be able to liquidate it. If it's a good dividend-paying stock and you have it for the income, you want to keep it. You just want to delta hedge that portfolio. The math will work out a lot better. You can find a delta that's deep in the money that you can hedge with that minimizes your costs in doing so. So you can manage your gamma to a certain level. You can't get rid of your gamma if you're going to be delta neutral. The only way to get rid of gamma is to say, well, I'm not even going to bother. I'm just going to own shares that has 0 gamma. I'm just going to own stuff that moves with itself, as opposed to anything that has a delta less than 1. As soon as you do, you're going to be you open yourself to gamma risk, but you can manage the level of gamma depending on how you want to hedge. All right, so let's see what gamma does to improve our estimate of how an option value changes as the underlying changes. And this looks intimidating, but it really isn't. What do we have up here? This is the call value, the new call value minus the old call value. So this is the price of the call after a price move of the underlying minus the price of the call before. So this is just the change in value of the option of the call is approximately equal to all of this. Well, what is this? This is the change in price of the underlying times the delta of the instrument that we're holding. Well, we knew that. We already figured that out. We already knew that. So if the change in price was $1 and the option has a delta of 0.5, the value of the option should change by 50 cents. Great. Plus, look at this term. It's gamma over 2 multiplied by the change in the underlying squared. The squared term gives us a nonlinear element to this equation, and it approximates the price of the call. So delta would just give us a linear relationship. So for small changes in the underlying, it was fairly good. But as we keep moving further and further away from that, delta combined with gamma comes very close to approximating what the call would be, to the point where you would say, well, it's pretty precise. All right, let's move on to theta. Theta is one of those things that just happen. It's time. It's the passage of time. And here's one thing I'm absolutely certain about. I don't know much about anything else, but I'm certain about this: time will pass, which means theta will happen. It's almost, well, I shouldn't say almost, it's deterministic, period. It is a change in the value of the call and the put, or the change in the value of any option, for a change in the time to expiration. If we are long options, we have negative theta. Time is our enemy. So if I buy a 30-day call, tomorrow it's only a 29-day call, then a 28. I only got 28 days for it to work. Eventually I'll only have 20 days, then 10. So it's got to work within those 30 days. So I have negative theta. Time is against me. If I'm short options, if I sell options, I have positive theta. Time is my friend, because every day that goes by, those options decay in value. If I sell puts, every day they go by, they decay in value. So I can sell puts and have just a theta play. I could just say, listen, maybe that price is going to change, but it's not going to change in the next 30 days. So I can sell puts on it on the next 30 days and maybe buy puts for 90 days out. That means I'm making a bet that in the next 30 days that price is not going to move, but then it will. I can take positive or negative theta. Here's the rate of decay basically on an option. Let's go out 120 days. Let's call this the expiration date, and here we are now. So as 30 days go by, theta doesn't really help very much or hurt very much. As 60 days goes by, notice that it starts falling off. Theta is your worst enemy as time to expiration gets closer and closer and closer and closer. Those options will start to decay very, very, very quickly. The put has a bit of a slower decay. Well, not slower decay, but kind of like a less of a steep fall off at the very end. Theta cannot be adjusted by positions in the underlying. So if we're long calls, we cannot take offsetting positions in the underlying to hedge out theta. There is no hedging out theta. You either are long, or sorry, you either have negative or positive exposure to theta, or zero exposure. When I say zero exposure, if I'm holding a stock, there is no expiration date. I just go ahead and hold it. I don't have to worry about time working against me. If I'm long options, I got to worry about time. If I'm short options, I don't have to worry about time. Time is my friend. I just got to worry about the underlying moving. So how can we use theta as our friend if this is the case? How can we use theta as our friend in this case? Well, let's say that we're interested in a 60-day call. Here's the thing about the delta on the call. Let's say that I'm looking at a 30-day call, a 60-day call, a 90 and 120-day call at the money. The call will have the same delta across all times. So if I'm buying an at-the-money call, 30 days out, it'll have a delta of 0.5. 60 days out, it'll have a delta of 0.5. 90 days out, it'll have a delta of 0.5. 120 days out, you get what I'm saying, right? The delta is constant at that strike across all maturities. So if I'm making a bet on a 60-day call, I will buy a 120-day call. I only need 60 days, but I'll buy a 120-day call. Why? Because if I bought the 60-day call and I'm wrong, look at the decay that I get. So imagine that it was here. It would move like this, and then it would decay. I'd get fast decay, so that if I decided that I was wrong within 10 days of expiration, I lose quite a bit. But if I bought the 120-day call, I still have the same delta. So if the underlying goes up a buck, the 120-day call will go up by a delta of 0.5. The 60-day call will go up by the same delta. So I'll get the same delta out of it, but after 60 days, if I say, oh, I'm wrong, well, I'm out over here. I lose some value, but not the heavy, heavy value. So if you're ever going long options, you want more time than what you need, because there'll be salvage value. Never mind about your cost in. Yes, you'll pay more on the way in, but you get salvage value. If you buy just the amount of time you need, here's what you'll find. You'll be right probably on your move, but you'll always be wrong on your time. The option will expire, and the very next day, it'll do what it was supposed to do. Oh, yes. I can't tell you how many times that's happened where your options expire, and then on Monday, oh, there we go. For the sake of one more day, right? Always buy more time than you need. All right, let's look at Vega. Vega, not a Greek letter, by the way. So when we talk about the option Greeks, all the other four are Greek: delta, gamma, theta, and then we're going to look at rho. Vega is a star. I believe Vega is a star, right? Or is it a constellation? I forget. I think it's a star. But Vega is not a Greek letter, but we call it a Greek anyway. What does it measure? Change in the value of the call and the put, or change in the value of options for a change in volatility. If we are long options, we have positive Vega. If we're short options, we have negative Vega. Positive Vega means we're long volatility. Short options mean or negative Vega means we are short volatility. What does this mean? Well, when volatility increases, option premiums increase. So if we're long a call and volatility increases, the value of the call will simply just increase. So we can make money just by being long volatility. And if we have negative Vega and volatility drops considerably, the value of the options will drop as well, just for no other reason than volatility is dropping. So we can actually trade volatility by trading options strategically at specific periods of time. You should be buyers of options in periods of very low volatility, and you should be sellers of options in periods of very high volatility. Vega is based on future volatility, which is unobservable. And option values are very sensitive to Vega. So if we look at calls and puts, and here's volatility, 5%, 10, 15, 20, 25, the value, the premiums on these things explode nicely. One of the nice trades I like doing in high volatile environments is to wait until there's, let's say, some news that comes out overnight. Futures are way down in the morning. Things look really bad. For instance, the Brexit. When we had when the Brexit was around, there was heavy selling the very next day, which spilled over into the second day before it started to recover. But there was heavy selling. Well, what happens is if you take the S&P 500 index, you get an 80-point drop in the index. Volatility is going to jump significantly. If you think that, well, you know what, it's over. That selling is kind of over. It's kind of overdone. It was a big reaction. It's really not there. That's a great time to be selling options on the index. What's going to happen is the value of the calls and the value of the puts are going to increase dramatically, more than what they should be. So what I like to do at that point is I like to take a point here, and I'll go 50 points up and 50 points down, and I'll sell a call. And I'll sell a put on this one, and there'll be huge fat premiums on this. Well, if volatility does die down, we're going to get something that looks like this, and then this will start to drift. Now, I don't have to worry about it hitting this price or hitting this price. All I have to worry about is the VIX settling down. Is volatility settling down? The premiums will come out of the call. The premiums will come out of the put. Since I'm short the call and short the put, I got to rebuy them. As long as the price drops, it doesn't matter. So if volatility begins to drop after this event, even if this starts moving towards one of the strike prices, as volatility drops, that drop will outweigh the move of the underlying, thereby making me money on just the drop in volatility on these. I like doing those kind of things. The other thing I like doing is options on the S&P expire weekly. You have weekly expiration on the options. So if there's a big report on a Friday morning, I like to take positions, long calls and long puts. So I might go long a call, long an at-the-money call, and and long an at-the-money put. So let's say the S&P is at 2100. And I know that there's a big report on a Friday morning. On a Thursday around sometime in the afternoon, because the daily premiums come out sometime in the afternoon. When I say they come out, that means the decay kind of happens in the afternoon. I'll look at the strike and I'll buy a call and I'll buy a put on this, because all I want the next morning, all I want to happen is volatility in front of that report. I want the report to come out and be volatile so that the market reacts either very positively or very negatively to that. So that volatility stays there. I'll be able to buy this call and this put really cheap, and all I need for them to do is one of them to explode. It doesn't work all the time, but when it works, it pays off nice. It pays for 3 or 4 times that it wouldn't work. So using options to trade volatility is fun. And finally, the last and the least, the most boring, row. It is a change in option values for a change in the risk-free rate. And over the last 5 or 6 years, has row been of any consideration to anybody? No, not at all. If you have calls, you have positive row. If you have puts, you have negative row. And here's why. If we're carrying an asset to some future point in time, it raises the cost of carry. As the risk-free rate increases, it raises the cost to carry. If it raises the cost to carry, it raises the price of the call. And if we're discounting back the strike price to today, as we do in a put, it lowers the present value of the strike price as the risk-free rate increases. So what happens as interest rates, or as the risk-free rate increases, it tends to increase call prices and decrease put prices. Row is it's not that interesting. It's really not that interesting. It hasn't been interesting for a very long time. And rates just don't change fast enough at any kind of rate, or significantly fast enough to have much of an impact on very, very much. Well, this is our last learning objective in this very long reading, and it is only one screen long, and we're talking about implied volatility. And I've alluded to this earlier. When we look at the volatility measure, we need some measure of forward volatility or future volatility. Well, it's unobservable. It's not a matter of that it's unobservable. It hasn't even happened yet, so it is in its truest sense unobservable. It's not that it's hidden. It's unknowable and unobservable, but it's estimatable. Volatility can be estimated from historical data. In the BSM model, volatility is future volatility, however. So a past estimate might give us some idea of what the future volatility would be, but the price that we see in the market will reflect what the market believes volatility is. So if the price that we see is not the same price that we get when we put in historical volatility, do we say that the option is wrong? Or do we say, the market must be pricing in a different level of future volatility? That's typically what we say. So that, in essence, no option price is ever wrong. It's just the implied volatility is right or wrong. Okay? I want you to think about it. You can't look at an option price and say that's the wrong price for the call. You have to look at what the implied volatility is at that price, and then you can say something about that volatility, saying, that's the wrong implied volatility. So volatility can be inferred from prices. That's called implied volatility. It is common to see different implied volatilities for different exercise prices, for different times to expiration, and different positions with the same terms. In other words, puts and calls. So if we see different volatilities for different exercise prices, that's sometimes referred to as a volatility smile or a volatility skew. For different times to expiration, and that leads into something called the term structure of volatility, and for positions with the same terms. In other words, for puts and calls with the same terms. So the same strike and the same time to expiration, the puts and calls might have different volatilities on each one. Options are sometimes quoted in volatilities, and when we quote them in volatilities rather than price, this is where we can say that's overvalued or undervalued in terms of the volatility. So if the option is pricing in too much volatility, we can then say, based on that measure of volatility, the option's overpriced. Rather than looking at the dollar value of the option, look at the implied volatility. So let's take a 3-month at-the-money call at 19% implied volatility on an index, and a 1-month in-the-money put at 24% implied volatility on a component of the index. How do you compare this? Never mind that we got implied volatility. Let's say that we didn't. And let's say that you saw the price of a 3-month at-the-money call and you saw the price of a 1-month in-the-money put. How would you know whether any one of these are overvalued or undervalued with respect to each other? One is a 3-month, one is a 1-month. One's at the money, one's in the money. One's a call, one's a put. Hard to compare them. But if we compare them on implied volatility, the call is pricing in 19% implied volatility. The component is pricing in, the put is pricing in 24% implied volatility. So if we had a belief that the index is going to be far more volatile than what's being priced in, we think 25% volatility on the index, but that the component will only be 20% because it's more defensive. Well, look at this. This implied volatility is 19. We think it's going to be 25. We want to be long volatility. We want to buy it at 19 because we think it's going to 25. This is 24% volatility. We think it's going to 20. It's easy enough to see that we want to sell volatility at this point, right? So what do we want to do? We want to buy the index call. That puts us long volatility. We want to sell the component put. That puts us short volatility. Nice and easy to do. So looking at it in terms of the implied volatility gives us a better idea of whether or not a call or a put is underpriced or overpriced based on what we believe future volatility will be. That's it. That wraps up this reading.